with activities in the field of chemistry and chemical education to improve the quality of chemistry education and expand cooperation networks.
We produce graduates who are competent and innovative in applying knowledge to solve chemistry and chemistry education problems, continually polish and grow their professional capabilities for their personal development and the betterment of society, both at national and international levels, and practice ethical principles and entrepreneurial mindset within professional and societal context. The following is the organizational structure of the Chemistry Education Study Program of Teacher Training and Education Faculty. We are led by a head of study program and supported by the management team. The Chemistry Education Study Program of UNS is accredited A by the National Higher Education Accreditation Agency and supported by 16 qualified teaching staff, including doctors and professors. Our teaching staff are productive in writing and publishing journal articles in reputable and indexed national and international journals. They have written several books and have been granted patents for their inventions. Reorganized and over to accredited journals, Jurnal Kimia dan Pendidikan Kimia, JKPK, a journal in chemistry and chemistry education, and Jurnal Pendidikan Kimia, JPK, a journal in chemistry education. Our teaching staff are active in conducting leading research in the chemistry education. Our study program is located in Building D of the Teaching, Training and Education Faculty to support our duties and functionality, as well as the teaching and learning activities. Various adequate facilities are provided. Teaching staff and administrative staff rooms. Comfortable and representative classrooms. Meeting rooms. Secretariat room for Chemistry Education Student Association, Covalent. Laboratories, which include 1. Analytical Chemistry and Basic Chemistry Laboratory, 2. Physical Chemistry and Inorganic Chemistry Laboratory, 3. Organic Chemistry and Biochemistry Laboratory, 4. Research Laboratory, 5. Fermentation Laboratory, 6. Learning Media Laboratory, and 7. Micro-Teaching Laboratory, as well as other facilities such as sports arena, sports field, and central laboratories. Our teaching and learning activities are conducted in 3 models: face-to-face learning, laboratory practicum, online learning. We prepare compulsory activities for students such as fieldwork lecture, KKL, real work lecture, field experience practice, and Seminar in Chemistry. We also prepare other activities such as webinars, our flagship programs include visiting professors, guest lecture, student exchange, national seminar in chemistry and chemistry education, as in KPK.
Bu Norma, jam berapa dimulai?
We collaborate with various national and international institutions. Our students, through Covalent, are committed to carrying out various activities that bring benefits to community, such as to help to solve activities include competition in the village school, basic daily needs, socialization program, various of activities including chemistry competition seminar. Our students alumni association, a home fraternal bond.
Namanya Kimia dan si pendapat dan
Service nation control in advancing Indonesian education.
Assalamualaikum warahmatullahi wabarakatuh.
The Honorable Vice Rector for Academic and Student Affairs, Universitas 11 Maret, Professor Ahmad Yunus.
The Honorable Dean of the Faculty of Teacher Training and Education, Dr. Mardiana.
The Honorable Chairperson of the International Conference on Chemistry and Chemistry Education, IC3E 2022, Dr. Budi Hastuti. Our keynote speaker, Professor Mauro Moscerino, PhD, from Curtin University, Australia.
Professor Chris Trainer from University of Leeds, United Kingdom.
Associate Professor Iyanatul Khairah, University of Nottingham, Malaysia.
Dr. Sri Mulyani from Universitas 11 Maret, Indonesia.
Dr. Sri Yamtina from Universitas 11 Maret, Indonesia.
And our invited speakers, Yuli Rahmawati, PhD from State University of Jakarta, Indonesia.
Dr. Muhammad Mashkuri from Universitas 11 Maret, Indonesia.
And Dr. Maria Ulfa from Universitas 11 Maret, Indonesia.
First of all, let us thank God for His mercies and blessings to enable us attending the first day of International Conference on Chemistry and Chemistry Education, IC3E.
My friend Kamila Farah and I, Satria Aji, will be serving as Master of Ceremony for Day 1 of the IC3E 2022.
I would like to welcome all the speakers, presenters, and fellow participants
to our conference. the first international conference on chemistry and chemistry education with the theme Reorienting Chemistry and Chemistry Education, Advancing Sustainability Research in the 21st Century.
Due to the post-pandemic situations, all sessions of the IC3E 2022 are virtual or remotely held. It is a pity that we are not able to invite you to visit our lovely city, Solo.
Allow us on this special occasion to highlight the agenda of the IC3E of 2022, Friday, August 19, 2022. The agendas are opening ceremony that we already done.
Anthem Indonesia Raya.
And the next agenda will be opening remarks from our chair.
Let's start this ceremony by pray first. Pray, begin. Pray, finish.
Okay, ladies and gentlemen, we will hear the national anthem of Indonesia, Indonesia Raya. Thank you very much. The next agenda is remarks from the Honorable Vice Rector for Academic and Students Affairs of Universitas 11 Maret Indonesia, Professor Ahmad Yunus. To Professor Ahmad Yunus, time and place is yours.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, ladies and gentlemen. My peace and God blessing be upon us. The Honorable Dean Faculty of Teacher Training and Education, Bapak Dr. Martiana, and also for Vice Dean, Faculty of Teacher Training and Education. The Honorable Speaker, both from overseas and from Indonesia. The Honorable Chairman of this conference, Ibu Budi, and also the Chairman of the Study Program of Chemistry Education, Dr. Sri Mulyani, and Master Degree Program, Ibu Dr. Yamtina, and the Coordinator, Ibu Dr. Nurma Yunita. It is great opportunity, and I welcome you all the first international conference on chemistry and chemistry education held from August 19 to 20, 2022, organized by the Chemistry Education Faculty of Teacher Training and Education, Universitas 11 Maret. On behalf of UNS and the committee, let me express my warm greeting and appreciation to all speakers and participants who involved in this conference to share their knowledge, experience, and work related to the natural applied education science. Ultimately, it is an honor for us to have an opportunity to organize the first international conference on chemistry and chemistry education. The rapid development of science and technology has long facilitated advanced in industrial and domestic activities, which later improve the quality of human life. For instance, we can now readily reach long-haul destination shortly due to the sophisticated air transportation in combination with the properly designed aviation fuel. Moreover, highly developed medical and pharmaceutical technology can suppress the mortality rate and prolong life expectancy in healthy society. Unfortunately, unsustainable manufacturing and human activities negatively affect nature as well. A constantly increasing demand for the commodity due to the rapid expansion of the human population has forced excessive nature exploitation. This led to environmental degradation and resource depletion, which can seriously impact to our life, such as global warming, flooding, low quality of water and air, the emergency of new disease, and many other negative consequences. This problem needs to be addressed by implementing sustainable production and manufacturing. Achieving those goals require consolidated strategies and solutions from various disciplines. Additionally, we realize that introducing sustainable issue in education is instrumental to awakening awareness of sustainable development. Therefore, this time, the committee selected the theme Reorienting Chemistry and Chemistry Education, Advancing Sustainability Research in 21st Century, as the theme of this conference. The International Conference on Chemistry and Chemistry Education will provide a platform for multidisciplinary discussion and sustainability issues. This conference does not only accommodate the most recent progress in the field of chemistry and chemistry education, but also in engineering, medicine, pharmacy, physics, biology, food chemistry, and mathematics to find solutions in sustainability research to support the sustainable development goal. Furthermore, this conference will also bring fruitful communication among the scientists, educator, engineer, medical doctor, and stakeholders to face the challenge in the sustainable development. Let me wish you all an exciting and intriguing in this conference meeting. With the say Bismillahirrahmanirrahim, the International Conference on Chemistry and Chemistry Education and held from 19 to 20 August 2022 is open. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you to Professor Yunus to already give the remarks and to formally open International Conference on Chemistry and Chemistry Education 2022.
The next agenda is a report from Chairperson of the committee, Dr. Budi Hastuti. To Dr. Budi Hastuti, time and place is yours.
Thank you, Kamila. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. The Honorable Vice Rector for Academic and Student Affairs, Professor Dr. Ahmad Yunus. The Honorable Dean on Faculty Teacher Training and Education, Universitas 11 Maret, Dr. Mardiana. Also, the Honorable the Head of Department Chemistry Education, Faculty Teacher Training Education, Universitas 11 Maret, Dr. Renat Sri Mulyani. The Honorable Keynote Speaker, Prof. Mauro Monserino from Curtin University, Australia. Good morning, Mr. Mauro. And the Honorable Keynote Speaker, Prof. Grace Rainer from University of Leeds, UK. The Honorable Keynote Speaker, Associate Prof. Dr. Inayatul Khairah from University in Nottingham, Malaysia. And also the Honorable Keynote Speaker from Universitas 11 Maret, Dr. Sriam Tinah and Dr. Renat Sri Mulyani. And also the Honorable Invited Speaker, Dr. Yuli Rahmawati from Universitas Negeri Jakarta. And from Universitas 11 Maret, Dr. Maskuri and Dr. Maria Ulfa. The Honorable Parallel Speaker, invited guests, Honorable Organizing Committee members, and all distinguished guest participants of the first International Conference on Chemistry and Chemistry Education, IC3E 2022. It is such as a great pleasure to welcome you all to the first International Conference on Chemistry and Chemistry Education 2022. On behalf of the organizing committee of the International Conference that will be organized by the Department Chemistry Education, Faculty of Teacher Training Education, Universitas 11 Maret, on 19 to 20 August 2022. The term for IC3E 2022 is Reorienting Chemistry and Chemistry Education, Advancing Sustainability Research in the 21st Century. This international seminar is scheduled to be held annually by inviting reputable domestic and foreign academics. The conference will be held online via Zoom meeting or video conference. And we hope the next year IC3E can be held via offline. About 100 articles will be presented to this conference, which come from presenters from Indonesia and foreign countries. And the paper will be published in Egyptian Journal of Chemistry, Proceeding of Scientific Net, and the CKPK, Jurnal Kimia dan Pendidikan Kimia. IC3E will discuss research result in the field of organic, inorganic, physical, and analytical chemistry, as well as other fields related to chemistry, such as pharmacy, health, energy, material, environment, and also chemical education research, such as models, approach, and evaluation in science learning. Finally, I would like to express my deepest gratitude to everybody that helped to support and taking a part in this conference. Keynote speaker, parallel presenter, participant, organizing committee, steering committee, the university, and also everyone else. Even though we in the committee have tried our best effort, I believe that there remains some inconvenience. For that, we do apologize. That will be in the end of my report. I hope you can enjoy the conference today until tomorrow. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Dr. Budi Hastuti, for the opening remarks and also event report.
And for the participants, please do open the chat box. There is a format name for presenter, co-author, and non-presenter. Please follow the code that is already given. Thank you very much.
We are now continuing our meeting to the next agenda. That is to listen the presentation from our first keynote speaker, Professor Mauro Moserino, PhD from Curtin University, Australia, led by Dr. Nurma Yunita Indrianti from Universitas 11 Maret as a moderator. Before we start the presentation session, I would like to introduce our moderator. Dr. Nurma is a lecturer from Chemistry Education Study Program at Universitas 11 Maret, Indonesia. Her areas of expertise are science teacher, curriculum innovation, and blended learning. Without any further ado, ladies and gentlemen, please welcome Professor Moserino and Dr. Nurma.
Okay, thank you very much, Camila and also Aci, for the time. Good morning, everyone. Good morning, participant, and of course, good morning to Professor Mauro Moserino. In Perth, still morning, right? Prof.
Yes,
Moserino.
good morning.
Yeah, okay, good morning. I would like to say good morning to our Vice Rector, our Dean of Faculty of Teacher Training and Education, our the Head of Chemistry Education Department, the Chairman of the IC3E, and of course, our participant here. In the first panelization, I would like to present you our first keynote speaker, Professor Mauro Moserino. Before I'm going to share about the things that we can discuss in this session, Prof. Mauro Moserino would like to have 1 hour talk regarding virtual reality, and also we will have 30 minutes discussion after that. Okay, about the Professor Mauro Moserino. Professor Mauro Moserino, PhD, is a professor in the School of Molecular and Life Sciences, MLS, at the Faculty of Science and Engineering, Curtin University, Australia. As we can see here, the areas of expertise in chemistry and of course in organic chemistry. Professor Moserino is one of the top scholar in the field of chemistry education. We read many publications of him in a Journal of Chemical Education in Science Education, and in 2022, we can see that one of the publication is very interesting regarding analysis and characterization of student interaction in a remote laboratory. This is the as adaptive research, yeah, because the pandemic. And in 2020, Professor Mauro Moserino, with his team, yeah, he has a book chapters entitled Multimodal Affordances of Immersive Virtual Reality for Visualizing and Learning Molecular Interaction. And this is the title, the theme that we would like to hear from him today regarding visualizing chemistry concept using immersive virtual reality. Yeah, that's an introduction about Professor Mauro Moserino. Okay, Prof. Moserino, now time is yours. Have 1 hour before we come to the discussion, please.
Thank you very much, Norma.
Yeah.
And thank you to the organising committee for this wonderful opportunity. I am quite honoured to have this chance. And I hope what I present today will be both interesting, stimulating and useful. So thank you very much for this opportunity. I will share my slides if that's okay. If I find the button that says share slides. Share screen. Okay.
Mm-hmm. Yes, it's showing already.
I will show it on. So you've got the full screen now?
Mm-hmm.
Okay, excellent. What I'll do to start with is I'll give my acknowledgements, because sometimes when I get to the end, I forget. So the people on the slide here, you'll see who I've worked with. The people who have done most of the work, in fact, are the two PhD students, Henry and Dewi. Dewi is from Indonesia, and they've been real champions with the work that they've done. Mihai Wan is the team leader in this project, and my other collaborators, David Trigas, who I'm sure you know, has been a long-term collaborator with me. I've learnt a lot from him. Roy Tasker and Chin Chung Sai are two others. Roy is from Sydney and Chin Chung is from Taiwan. So that's a team. And we were very fortunate to have an Australian government research grant on this project, and they've been able to pay for Henry and Dewi's tuition and scholarship, and also for visits from Roy and Ching Chung to come to Perth. Okay, what I will do today, I will start with a brief overview of visualization and immersive virtual reality. As part of this project, we have developed an immersive, or we've applied an immersive learning experience framework to our study and how we've developed our virtual reality programs. And I'll give you a taste of 4 small studies in virtual reality, 2 on snowflakes, one led by Dewi and the other led by Henry, and then a little bit on a taste receptor, and finally just a taste of the protein substrates. I'll give a summary and then we'll open up for questions. Okay, visualization. This is a critical component for chemistry, and you may have seen this triangle before, commonly known as Johnson's triangle. And the issue is that a lot of students, to understand chemistry and have a good feeling for chemistry, they kind of need to be able to transfer from these 3 areas, being able to link the macroscopic, what we see and measure, with the submicroscopic, what's actually happening at a molecular level, and the symbolic, the way we represent and describe those phenomena. And these transitions between areas is very difficult for many students, very difficult for many of us. But learning to do that is key. And so what we were looking at is we wanted something to help the students to make those sort of transitions. Often when students are learning chemistry, they will learn on the basis of, they'll think about the symbolic, because that's often the way we teach it, and sometimes a little bit on the macroscopic in laboratories and observations, but not so often in the submicroscopic, because that's very hard to see. And many students learn chemistry, if you like, on paper. So they've learnt the chemistry on paper, where they know how to deal with the symbolism, but they really don't have an understanding of what's happening in the flask or in reality. And so what we wanted to do is develop something that helped them tie all three concepts together. So what we chose was immersive virtual reality. This is a fairly new technology. It's come out almost 20 years ago now, but it's only recently that it's become fairly sophisticated and also reasonably cheap. Reasonably, I say. And so we chose virtual reality because it allows the students to enter a virtual world. When you put these goggles on, the outside world is blocked from you. And in this picture here with Henry and Dewi and the snowflakes activity, once they put the goggles on, all they saw was a snowfield. They couldn't see the outside world, and so they were immersed into this area. So they had this visualization, and then they could see things that you can't see in reality. We can't see water molecules in reality, but in virtual reality, they can see them, they can handle them individually. So that was part of the reason why we chose it. And so this slide basically says what I've just said. Your physical models are static, and you can't use, in the physical models, if you're making a molecular model, it's very hard to do something with 100 atoms or 1,000 atoms, whereas in virtual reality, that's not a problem. With the computer simulations on the two screens, yes, you can use more molecules, but you're always looking at it from one direction. Even though you can roll it around a bit, it's not so natural. Whereas the virtual reality will teleport you into a new world, and you get to see things that are much more complicated, and you can interact with those things to a much greater extent. So what we did, we developed 3 virtual reality programs. One was on snowflakes, where we asked the students to the question, why do snowflakes have hexagonal symmetry? And the idea of this activity was to help the students learn about intermolecular forces, particularly hydrogen bonding, and how it works, and how hydrogen bonding affects the structure of ice. The second one we developed was a taste receptor, and the idea here was to teach the concept of stereochemistry and intermolecular forces between substances to learn those concepts. And we use taste as a context to do this. I'll talk a bit more about each of these later. And the third one was an enzyme substrate, where the students would explore an enzyme and the substrate and how the substrate interacted with the active site. And so they would be exploring very complicated molecules. Okay. I think I need to use my mouse. Okay, so when we were developing the activities, we used Deed's immersive interface as our guiding principle for how we did our activities. And each of the activities, we would try to incorporate sensory components, actional components, but also the activity had to have some sort of narrative and a learning sequence, and there was social interaction. All our 3 activities work with pairs. So the idea is 2 students do the activity together and they work. So in the sensory, I'll give you some examples of how we did this for each of them. Typically with virtual reality, 3D representation, visual, you can see it, you can hear it, and sometimes you also have haptic feedback. So if you get the structure right, it will vibrate or something of that effect. Actional aspects of it, we can get the students to move around or actually move the activities, make molecules, so they're doing things, not just watching. Again, they have to have a story and a reason for doing this. So we set targets within the activities to try and guide them through. And at all stages, we were encouraging students to talk to each other, explain out loud what they think, check with your partner, etc. So how do we actually do this for each individual area of DEED's framework? For the sensory and the actional, we asked ourselves often, always, what can we do better with the technology? So we weren't interested in doing, we're trying to do things that you could do with virtual reality that was really very difficult to do with anything else. So that was the premise. And so we wanted to visualize the molecular world in chemistry. And again, that's much easier to do in virtual reality than most other technologies. Traditional media could show 3D structures, but they're on a flat screen and you had to rotate it around with a mouse or something like this. And it wasn't really the same. And in the snowflakes crystals, we had the students working with hundreds of water molecules. In the taste receptor, they had looking at the stereoisomers and how well they fit in the receptor for the reaction, and the enzymes, they were observing and exploring the structure of the enzyme, the active site, and how things would work. So when we looked at the actional, what did we do there? Again, looking at how we can do this better with virtual reality. We wanted programs where the participants could do things. No, we wanted programs where the participants had to do things. So it wasn't necessarily optional. It was a part of that program. They had to build a molecule. They had to move a molecule from A to B, or insert something in the appropriate site, build a structure. And that was actional. So they were learning not only by watching, but they were actually doing and putting them together. Virtual reality has an advantage that they're natural activities. They're hand controllers. If you wanted to catch something, you just use your hand to pick it up and the controller would pick it up. And what the students would see, they couldn't see each other's body, but what they could see was the headset of their partner, and they could see their own hands and their partner's hands, and they looked like hands on the virtual reality. So when you were going to pick something up, you move your hand forward, you could see your hand, and you press the trigger and your hand closes on the object, and then you can turn your hand and you move it around. So they were natural orientations, not like on a computer screen where you're moving a mouse or keys to rotate structures. So in the snowflakes activity, they were building, putting together molecules to build a lattice. In the taste receptor, they were building the two enantiomers and placing them in the taste receptor. And in the enzyme, they were taking the substrate and moving it through the enzyme into the active site and placing it in the right place. So all these three activities had a required actional process where they had to do something. The narrative of these sort of things, we had to have a clear learning objectives and goals when we were putting these together. And we wrote a storyboard of what activities they were doing and how they were going to learn from those activities. And so, for example, in the snowflakes, the focus was polarity, bonding, and structure with water molecules. So it was a hydrogen bonding lesson. With the taste receptor, we're looking at structure and reactions to taste sweetness. Again, in this case, stereochemistry played a part, but also intermolecular forces where dipole and polarity interactions and understanding how they played a part in determining why one enantiomer was sweet and the other one was not. And in the enzyme, again, we're looking at structure and polarity, identifying the appropriate regions in an enzyme and having the complementary enzyme positions to bind to the substrate. Each of these activities come with pre and post interviews. So they were interviews, the pre were to get an idea of what they actually knew, but also to give them information that they may need or get them thinking in the right way for the activity. The post interviews were a reflection or analysis of what they actually learnt and how they felt from doing those activities. And the social action of the program, the students were encouraged to think out loud and integrate what they were knowing to build scientific understanding. The students would talk to each other. There were often questions provided to the students during the activities in the program, not from us outside the activity, to challenge them. How do you think this is happening? Explain why this has happened. Check with your partner. Think out loud. So those sort of things were there to allow that social aspect of learning, because learning is a social activity, and to try and get them to do that sort of thing. And the pre and post interviews were all done in a collaborative manner as well. We didn't interview the students individually. They were there together and they talked to each other. So I'm going to go through now some studies of what we did. Keep an eye on the time. Okay, so the first study I want to talk about is Dewi's project. Part of Debbie's project. She's done a lot of work. I'm just picking a few small pieces. And part of her project was to compare 3 different media for learning hydrogen bonding. And so the 3 media we had physical models, these things here that you see in the red and white structures. These were models of water molecules that were magnetic. So the hydrogens were one pole and the oxygens were the other. So they were attracted to each other, and hydrogen would repel each other. And so the second variety was a computer simulation, and the third was the immersive virtual reality. And so we wanted to know whether what we could learn from something that's simple hands-on, something that was using computer programming model of 2D and the virtual reality, and how they were different. So the objectives were what are the affordances and limitations of each learning media, and how do students learn molecular interactions and structure using the learning media. So what we did was, these were the learning objectives for the activities overall. And what are the things we want them to know when understanding hydrogen bonding and intermolecular forces? And so concepts like electron density was something that was a key idea. Concepts of attraction and repulsion, obviously hydrogen bonding and what it is, the idea of bond energy and the concept that you need energy to break a bond, the dynamics of hydrogen bonding in liquids, that it's not a static thing, optimal angle and distance. So when a hydrogen bond is formed, there is a preferred angle and a preferred distance, so they could explore that. The tetrahedral nature of hydrogen bonding around a single water molecule, hexagons in the ice lattice, the concept of scale and how big or how small atoms are and molecules are. So therefore, even a snowflake, how large that is on an atomic scale. The 6-fold symmetry and environmental factors that would affect the snowflakes. So on this diagram here, we're starting with, on the left-hand side of the slide, you kind of need to know into your polarity of the water molecule. Then we're going into hydrogen bonding and tetrahedral nature, the lattice of ice, and then finally the ice crystal. So that's how those learning objectives kind of flow. And the way the activity worked was that in a 2.5-hour session, the students would start with a pre-interview to find out what they understood about snowflakes and what they understood about hydrogen bonding and water. And then they did the magnetic model kits, and then there was a post-interview. This post-interview was to review what they'd learnt and how their understanding changed from the pre-interview, but also to give them some questions to prime them for the computer simulation. And each of these three activities, we're kind of designed to give the same thing, but not focusing on exactly the same. As you can see from the color coding in the middle here, the light colored ones are what we expected to learn from the magnetic models. The intermediate colored ones are for the computer simulation, and the wine colored ones are for immersive virtual reality. So that's what we expected to learn. And obviously some things were covered in all three, hydrogen bonds and optimal angle and distance, but some were only covered in one. The dynamics of hydrogen bonds in liquid we felt was best learnt only in computer simulations. And then we had a post-interview to find out what they thought about not only the virtual reality, but the whole activity. Okay, so what we did, preliminary analysis. We used quantitative analysis as general inductive approach. Each session was video recorded. We had cameras recording the activities, the pre-discussion. The students wore microphones, so we had their voice recorded. We also had them drawing pictures and used those as a guiding what they understood. And we looked at the topics, how they were discussed and the frequency in which they were discussed. And the numbers range from 1 to 36. We applied the immersive learning experience framework for each of those activities in part of analysis. Although this immersive learning experience framework was designed for virtual reality, we found that it actually worked for even magnetic models and computer simulation. So this is effectively what was happening. We'd have a pre-interview, and each of the activities had a pre-post interview that was small to just get an idea what was going on, and then there was a final post interview. Okay, what did we find? When we're looking at their prior knowledge, explain the shape of snowflakes and draw the interaction between water molecules at low temperatures. So what we asked them to do here was imagine a water molecule, draw the structure of a water molecule, and then imagine a second water molecule coming into the first at low temperatures, approximately freezing point. How would they interact? Draw that interaction. And then, is there a third possible water molecule? Can a fourth one come in? Can a fifth one come in? How many can come in? And then they come to an idea of the maximum number of hydrogen bonds. And so these are the sort of things. Most students had a reasonable understanding of hydrogen bond, the electron density, attraction repulsion, and hydrogen bonds. None of them mentioned bond energies or the dynamic nature of hydrogen bonding. The optimal angle and distance were hardly mentioned, and tetrahedral also not very common. Hexagons, I had no idea the lattice at the time, or only a few. None talked about the scale. Some talked about six-fold symmetry because they were showing the picture of a snowflake, and they said that there must be some sort of six-fold factor. And some, again, not sure how, but the environment must be affecting why they're different. Okay. So when we're doing the magnetic models, the things in dark here are what we were expecting. Expecting them to learn from this magnetic models. And so they were playing with these here, and this is a couple of images of what they were doing. The top image, the students recognizing that hydrogen and hydrogen don't form an interaction, they repel each other. A couple of students at the beginning, when they said, I don't know how they interact, but if it's hydrogen bonding, it must be the hydrogens interacting with each other. So they drew the two water molecules, the hydrogens interacting with each other. And this is what the student was doing. So I was expecting them to interact, but when I put them together, they don't, they repel. So that was obviously not a correct assumption. And then they work out how it should work out. So when they were doing this, they had haptic activities. They could feel attraction, they could feel repulsion, they could see 3D structures. They quickly worked out that one water molecule will form 4 hydrogen bonds with 4 other water molecules, and that shape would be tetrahedral. Some of them, many of them worked out that you form rings because they were putting the molecules together, and because the snowflake had symmetry, they were trying to form something that was a ring structure as well. And many of them said, well, it's very complex in that process. Again, with the magnetic models, the key, this is a diagram of them playing. This is the research setup we had. The researcher there is Dewi. These are the 2 students working away, and their diagrams, pictures of snowflakes. And they were using their sensories to shapes and colors and haptic. To colors recognized as an oxygen, and the white bits were hydrogen. The red is the oxygen and white is hydrogen. They were connecting, rotating, shaking the molecules to see what was happening. They were talking to each other, they were looking at each other's activities, seeing what they were doing, and in some cases, as a team, put structures together. And the main affordances were that it was simple, and the strength of interactions between 2 water molecules was clearly experienceable. They could see what was going on. Okay, when we went to the computer simulation, again, on the left-hand side in black is what we were expecting to learn from the computer simulation, and the right-hand side gives you an idea of what they were doing. There were sensory stimuluses, the images they could see a graph, and there were actional things in that they could move the slider bar across to change the angle, and then see how that energy changes in the graph. And they could move their slider bar to change the distance, and again see how the energy would change in the graph here. So there were actional things that they could do. They weren't just watching or listening to the process. And so again, under the 4 areas, the colors, it was dynamic, they had quantitative data that could see in the form of graphs, and there was actional components, and they were manipulating the parameters to see how things would change, and then learn about the importance of bond energies. And again, the main take-home message, what the students were doing here was, of the 3 media, this was the one that was probably most familiar with. They were playing with a computer program. Even though they hadn't used that program before, most of them were okay with that. They had text instructions, so the instructions on how to use the program were on the right-hand side, and they worked through those instructions and just followed the narrative. So one of the things that we noticed that with this one, there was very little exploration. Let's see what we can learn. It was, let's do step 1, let's do step 2, 3, 4, and finish that activity. So there was a bit of social activity, but the social tended to be, one person took over as the pilot who was driving the mouse and the keyboard, and the other one was just a co-pilot or a navigator telling him what to do. And the main affordances from the computer simulation that the students felt that they learnt principally from this program was that the dynamic nature of molecular interactions. They could look at the polarity map and see how, going the wrong way, how that changed by moving these things down. They could see how the polarity would change. they could see the hydrogen bonding forming. That's a dotted line here. And they were moving molecules around, etc. But the thing that they found that most amazing was that the simulation of the dynamic nature of hydrogen bonding and how it changed very rapidly. Okay, when we were working with the immersive virtual reality, we use the HTC Vive Pro sets. These headsets you put on, they're radio controlled, so there's no cable attached to the headset and the computer anymore. The early programs we had to use a cable, but now it's Wi-Fi. They had handheld controllers. They could move around an area that was about 4 meters by 4 meters. And the way the program works is that as you get near the edge, they will see a wire grid appear. So that tells them that they're very close to the edge. Don't go beyond that because you'll bump into the wall or something like this. So there wasn't a problem with them not knowing where the boundaries were. And they were sharing the space. They were both in the same area together, and there was social interactions. So this is what they actually did. There were 6 stages to this thing. The first stage was just entering the winter wonderland and observing the environment and playing with the VR equipment to pick up snowflakes and compare them. So they were just learning how to move around, navigate the area, and how to use the equipment. The second step was they were asked to make a hydrogen bond between 2 water molecules. So they get the 2 water molecules, bring them together and see how they interact and work out what's the best distance and arrangement. And you can see in this image here, in the central image, a little green bond there. That the color of that changed if the angle was not so good, and the thickness of that changed if the distance was not so good. So the ideal hydrogen bond should be green and thick. And so they were playing around, and they could see that if they pull it apart, as they were pulling the molecule apart, the bond got thinner and thinner, and then it disappeared too far away. And if they changed the angle, the bond changed colors from green through to red, and then disappeared when it was no longer forming a hydrogen bond. So they did that exploration. The following activity was, let's put them together to form how many water molecules can form hydrogen bonds around a central water molecule. So they were given one central water molecule. This is the one that's got the halo around it. And then a basket full of other water molecules that they could pick up one at a time and attach. And they quickly worked out that you could only form 4, and there would have been a tetrahedral arrangement. Having done that, we got them to build a sheet of ice, one layer thick, a layer of an ice lattice, by putting these clusters together. And again, here they had to demonstrate their understanding of lone pairs lining up with hydrogen atoms, etc. Having done that, we gave them 3 sheets, and they put the 3 sheets together to form a lattice of about 150 water molecules. And then they finished the activity by observing the lattice and seeing how that symmetry in the lattice could relate to the symmetry in snowflakes, and comparing snowflake structures with lattice. So when we did this, again, here are the things we expected them to learn. On the left-hand side, and this is an image of the sort of things they would see. And here are the hands of one of the participants, and the other participants are probably these 2, the head of one of the participants. Obviously, a participant can't see his own head or her own head. And they were using virtual space 3D structures, and they had haptic feedback. When they got it right, it clicked in this place and they could feel that click. They were creating structures, and they were walking around observing different structures. As an example, they see different things. We can see here that Jared from his view, he's looking and he can see his partner Gabby in the distance, but his view is looking more flat on, and whereas Gabby is looking more down onto the structure, so she is seeing the image below. So they were testing their knowledge by moving things around. Those who moved around a lot seemed to learn more than those who were just watching from one direction. And the main gain from this one was that they had the precise arrangement of atoms in a complex structure. So they could build a complex structure fairly easily and then study that with lots of molecules that is not so easy to do in anything else. They were walking around the molecules, and the people who were gaining most seemed to be walking most, rotating and connecting molecules. Again, these were natural activities. You want to move the molecule, you catch it and you turn your hand and the molecule moves. So they were some advantages. So summary of the sort of things that we observed. These are for the models, the number of times these topics were discussed for each of them. Now the colors, if they're black, they're okay, but the red and greens are the sort of things that were a little bit surprising. We expected a better interaction here because when they're doing the models, they can feel the energy required to pull them apart. They can, that energy that brings them together. We expected energy to be more of a discussion. It was not, so we weren't so, that was a surprising result and disappointing. And the simulation energy was a big part of the graphs. And again, they didn't talk about that. No one talked about it in IVR, but we weren't expecting it in the IVR activity anyway, because that was not part of their activities. And again, here, this was not expected, not part of the simulation, but they, many of them talked about the tetrahedral nature. So that was a pleasing result that we weren't expecting to get. Hexagons and isolators, again, we weren't expecting that because not something that was part of that activity, but many of them discussed that. So we got some unexpected positive results and some unexpected negative results, and the negative results are in a red, unexpected negative results. So in a summary here, the IVR is comprehensive coverage. They gave the students, they had a narrative to follow. They were using social, actional, and sensory components of the learning. There were emerging concepts that happened that we didn't expect, and they were the ones colored in green, and there were some of them that missed concept that we thought we would be getting, and they were the ones covered in red. Okay. Well, our implications for this study, we found that it should consider aligning the narrative, sensory, actional, and social immersion to better promote the comprehensive understanding. So they were still a little bit fragmented. The immersive learning experience framework works, and it works well for not only virtual reality that it was designed for, but it also works for the other two types of media. I think it's a good philosophy to follow with any teaching media that you're trying to do, and not just have people listen and read, but having them doing things and having them discuss things with others to bring that whole story together. In study 2 is Henry. This one here, we're looking at, Henry looked at all 3 activities, but we're looking here at how, investigate how collaborative, immersive virtual reality can help students improve their conceptual understanding of intermolecular forces and shape in chemistry. We had 3 activities. This one will focus a lot on their diagrams. So the objectives here is on snowflakes, what is the level of student conceptual understanding of intermolecular forces in snowflakes after collaborative learning experience? And how do students use immersive learning experience component to improve their conceptual understanding of intermolecular forces in snowflakes. Now, in this activity, these students are different to DEWI students. These students did not use molecular models and they did not use the computer-based program. They started with a virtual reality right from the word go. So we had 35 pairs of students. They were chemistry-related majors, so either majoring in chemistry or doing a chemical engineering or nutrition or something that requires significant chemistry. They all had completed Year 12 chemistry. The process was a design-based approach. So again, we adjusted the program slightly as we progressed if we discovered things weren't working so well. And the task was we're using prior knowledge of molecular polarity to explore the nature of intermolecular forces in snowflakes. And so the way this worked was they had a pre-interview, like in DEWI's case, and the pre-interview here was very similar to the one in DEWI's. Then they did the immersive virtual reality session. That was about 30 to 45 minutes. And then we had a post-interview to see how would they change what they said before and what have they learned. So just as an example of some of the things, what we did when we analyzed the information, we looked at the student-generated diagrams and we grouped them into three groups. People who had a high level of prior knowledge of hydrogen bonding, and so they would draw in their structures something showing a central water molecule with 4 hydrogen bonds, and the hydrogen bonds are linear, and there's hydrogen interacting with oxygen and lone pairs interacting with hydrogens, etc. Intermediate group with 32 students had the concept that they understood that hydrogen bonding was a hydrogen going to an oxygen, but they were not really aware of the role of lone pairs. And they were just thinking of the oxygen as a general delta minus area that was going to be attracting delta plus hydrogens, but they weren't thinking about the idea of lone pairs and hydrogens interacting, forming one hydrogen bond, not multiples. And the third group, which was really sad to see, there were 10 students who really had no idea. Even drawing the structure of water was novel, as this guy here has. They're not something that you would see in any textbook. So their understanding of what was going on was quite disappointing. Anyway, how did they progress? So what happened when they did the virtual reality? Before virtual reality, student explanations of the shapes of snowflakes were fairly comparable with most groups because most of them had no idea. And that's fairly understandable because it's not something we teach. And being in Australia, snow is not a key component of our lives. And so many of them had never experienced snow either. But the common explanation would be from a central water molecule, the hydrogens and oxygens would just keep adding to each other and spread out. That's why you have snowflake is a flat and structured. But they had no idea of much more than a general overarching explanation. After virtual reality, the students started to discuss intermolecular forces in 3D terms. The intermediate level of prior knowledge group seemed to benefit the most from this intervention. And after the VR sessions, a high level of prior knowledge students provided the most comprehensive explanation. So the intermediate and high level both advanced well. The poor pretty much stayed poor. So we look at the high prior knowledge group. When we're talking about the concept of hydrogen bonding, before virtual reality of this 28 students, 18 did not mention hydrogen bonding, 8 mentioned it, and 2 showed it in the diagrams. After virtual reality, 4 still did not mention hydrogen bonding, but 15 mentioned it and 13 changed their diagrams to show it. Similarly, when we're talking about the shape of snowflakes, 2 mentioned hexagonals at the molecular level. 17 said that they're branching out. 7 talked about, gave other reasons, but unspecified, and 6 said they had no idea. And after the virtual reality, 18 talked about hexagonal patterns. None of them mentioned the 2D nature and branching out. 12 had other factors, other reasons, and only 2 still admitted no idea. So there was a fair trend shift from this group. When we look at the, oh, okay, I must have skipped a group accidentally. The high, very quickly, the high group, 26 of them talked about the hexagonal nature, and only 2 gave other reasons. None says no idea. And even talking about hydrogen bonding, again, they were all mentioned it or adjusted their diagrams. The intermediate one I've just gone through. With the low level, before 10 of them mentioned hydrogen bonding, but none of them showed it in the diagram. Afterwards, 3 showed it in the diagram and 7 mentioned it. When we're talking about hexagons, again, 6 moved to talk about hexagons, but 4 still had either no idea or alternative conceptions. No, I'm sorry, I've got this wrong. For the progression of conception, the nature of the hydrogen bonding component, 10 had no idea beginning, and 3 mentioned it in their discussions. 7 still did not mention it. None of them showed it in their diagrams. So their diagrams did not improve at all with the low priority. So they didn't really learn anything about what hydrogen bonding was as a consequence of the intermolecular forces. So when we're talking about the sensory, keep an eye on the time, I think I'm going too slow. When we're talking about the sensory immersive component, the high and intermediate group actually used the cues. They recognized the thickness of the bond, they walked around, they engaged in the activity to a much greater extent. And a student comment here, well, when like it's on an angle, it's not lined up straight on with the hydrogen, it's weaker. And when it gets closer, it gets weaker. So they were talking about, the lining up. If it's not lined up appropriately, it's a weaker bond. So they're talking about the color here, and then the strength and the thickness. And here is again an example of it not lining up. So they're playing around with these things. The absence of a signal to show the attraction repulsion made it hard for students of low prior knowledge to create hydrogen bonds. So the low prior knowledge, because they didn't know what was going on, they didn't even get it lined up correctly, or they didn't notice this. The green stick or the hydrogen bond only appears if they're in approximately the right space, and the low prior knowledge people never got it into the approximately the right space. So consequently, they never saw that cue, or if they did, they didn't notice the cue, and they couldn't learn from that process. So one of the things we looked at also was the average time spent exploring molecules as far as the actional activity is concerned. And we're looking at 3 components here. The component where they're just exploring 2 molecules to form hydrogen bonds, creating the tetrahedral unit by 1 and determining how many go around it, and then exploring the lattice. And you can see here that when we look at this, the low prior knowledge only spent about half the time exploring hydrogen bonding than the other two groups. And they spent more time on creating the tetrahedral unit, probably because it took longer for them to complete the task because they didn't understand the hydrogen bonding process. And then when we're exploring the lattice, having put the lattice together, they again spent about half the amount of time that the high prior knowledge people did. So those who had better understanding played more and learnt more. And when we're looking at their understanding of their times they changed perspectives, so the number of times they moved around to look at things from a different angle. Again, the intermediate and high prior knowledge moved around a lot in the to forming the hydrogen bonding, exploring that concept. Here they're pretty much the same because they were just putting them around the one water molecule. But when we're exploring the lattice, again, you can see the difference. The low prior knowledge people hardly moved, and the high prior knowledge and intermediate were many times more, approximately 4 times more. So they were exploring the space and using that aspect of virtual reality. Okay. So final bit was the students' use the social interactions and how many times they exchanged turns to interact with the lattice, and the number of conceptual questions they were asking each other to try and understand. Again, you can see that number of conceptual questions, the high prior knowledge were actually thinking at that molecular level, what's going on, how could this lattice give us a snowflake? And so they had good conceptual discussions, whereas again, the low prior knowledge weren't even thinking at that level. The discussions they had were very simplistic. And the number of times they exchanged ideas or turns in playing with the lattice, so that was a real interaction. Again, the high prior knowledge used that component to a much better extent. So the main findings here is that the embodied actions really played a big part on how the students used the program and how they could gain from the program. So we try to encourage them before they start. You should walk around, you should explore. But some students, those who took that advantage, seem to gain the most. Students with different prior knowledge benefited differently. And again, that's not surprising. Those who know something can learn more easier than those who don't know. The immersive art should be used in combination with relevant pre-IVR activities, particularly for those who are weak in their prior knowledge. We probably should have had another activity for those who were in that bottom group to do something to build their understanding a little bit more, so when they went into virtual reality, they could start to gain what the others were gaining. And by combining technological and pedagogical affordances of IVR, we can get them to see things to quite a different extent and to unprecedented possibilities. And you'll see some of those in the next activities. Okay. Study number 3, these two will be quicker. Okay. How does shape play a part in taste? That was a question we asked the students. And part of this is stereochemistry. So students have difficulty understanding stereochemistry. They need to visualize the molecules in 3D. And often when we teach stereochemistry, focus on the shape. And this sort of diagram is fairly common in textbooks, where you'll see that the receptor site, which is the flat bit in the bottom, has got an orange square, a yellow triangle, and a green cylinder. And for the molecule to fit, those shapes need to fit into those holes. And so, and the example is the one on the left fits and the one on the right doesn't. So they're two enantiomers. So stereochemistry is playing an important part. But we never say anything about polarity. And so what we did, we gave them these two, we actually got them to taste these two molecules. They're food grade quality, so we had ethics to feed them this. And we checked that no one had any allergies before we did this. But L-phenylalanine is quite bitter and D-phenylalanine is sweet. And so we got them to think about why is the difference, and then they examined these in virtual reality. But the key component is that the electron density is an important component, because the carboxylate area is electron rich and the ammonium area is electron poor. And it's not just the shape, but it's the charge that determines what goes where. And when we teach stereochemistry and the impact of stereochemistry, we often don't talk about that. So our research question was, how does the student's understanding of the chemistry of taste of substances change through IVR on the taste receptor, and how do university chemistry students interact with IVR to build their conceptual understanding of taste of substances? So what we did, after they had the pre-discussion, we got them to construct the two isomers of phenylalanine. So we just gave them the pieces as construct a molecule of phenylalanine, and then we said, okay, you've made one, now make the mirror image. And then they had to determine which was D and which was L, having made the two. And then they construct electron density maps of the two stereoisomers, so identify the electron rich, electron poor, and non-polar regions. And then they went to the taste receptor and explored which of the two isomers would fit appropriately into the taste receptor to give a positive, to give a positive reaction. Okay, again, we had 29 pairs of students. These were the same pairs of students that we used in the previous activity for Henry's snowflakes. They had already done the snowflakes activities. Again, we video recorded everything, and we analyzed the videos and their actions to come to our conclusions. So what we did before IVR, we asked them, why did these two substances taste differently? We didn't tell them what the substances were at the time. The students were, 8 pairs were not sure, and the others gave reasons based on shape. So, for example, they're not sure, they're not exactly the same. They're not going to have exactly the same taste. I'm not really sure how that affects the taste. It's just they're not exactly the same, so they won't have the same taste. That's a typical not sure answer. And for those who talked about shape, they would use things like different conformations, other chiral molecules, and B conformation cannot fit into A receptor. They've got a specific structure, a right shoe and a left foot. So again, looking at the shape, a wrong chirality, then it can't be detected. So again, the focus of those sort of discussions was very much on shape. When they were in the virtual reality, this is how we analyzed the information. We had 2 cameras videoing what the students were doing. And so these are the top 2 here, and 2 images of what the students were seeing in their virtual reality. So we would put those 4 together and watch them to see, try and line up. Oh, what's it happen here? Let me see if I can go back. Yeah. Okay. And so you can see these 2. These were looking at taste receptor from above. Most students looked from above, but a few students explored and got down underneath and looked from the side to get a better view of what was going on. So they were using the virtual reality to a greater extent in some respects. We break these down into 3 groups of people. Category A generally had no difficulties with the IVR learning task. There were 22 pairs there. 4 pairs had some reasoning about shape and or electron density, but they struggle a little bit. And category C, they focused on electron density, but didn't consider shape at all. So it's an example of what they were doing. This is a typical example of the people who seem to know what was going on. There was specific shape because of the various pockets in the taste receptor were colored. The brown pocket is positive, which means it's electron poor. Yeah. And which means it will probably take the electron rich component. The yellow pocket is negative. It will take the electron poor. So they were talking about these things. The gray pocket has no charge. And then, yeah, sure. So like, yeah, it will need a specific fit. And so they talked about all 3 pockets and they were putting it together. Category B tried to put 2 molecules in the same taste receptor. 1 molecule fitted only of the taste receptor pockets, or they focused on only 1 receptor pocket. So here with the 2 molecules, I think because there were 2 students and there were 2 molecules, they each thought they had to put 1 molecule in each. So they missed the idea that 3 parts of a molecule need to interact with the 3 pockets in the taste receptor. A few students only included the polar components and didn't consider the non-polar component. I think that's partly because often when we teach intermolecular forces, we talk about dispersion forces as being a weak force. But electrostatic forces are quite strong. So they were thinking, they kind of didn't worry about the weak intermolecular forces and focused only on the strong electrostatic forces. And 1 student only put 1 receptor in 1 pocket. So we don't really know what was going on or what was motivating them there. And the third one, again, only focused on electron density. They weren't concerned about the shape, so therefore they were not looking at the non-polar bit. And again, I think that's because they were thinking that's not important. It's only a weak force. Okay. So when we're looking at this, irrespective of their difficulty, some students met. Most students, 28 of the 29, actually recognize the importance of electron density and molecular shape on taste receptor. So most of them got to the right answer in the end anyway. And opportunities to keep testing their ideas in IVR help build a better understanding. So it wasn't just have 1 shot and then see how you go. They tried something, said that's not quite right, you want to look at it again. And the program was often did not let them progress to the next stage until they had the right idea in the earlier stages. So they had to play around a bit. So some of the interactions they had, we look at the Carl and Craig. They struggled at first. So the benzene here is non-polar. So they had it sticking up, and then positive reacts with negative, negative reacts with positive. So they got that bit right. And then they're coming around by moving them around. They worked out because the L doesn't fit properly, the non-polar bit's sticking up. And so when they changed it to the D, they found that it all fits nice, and that's, whoops. And that's, I'm thinking, is a sweet one. So they started off with focusing on the getting the 2 charge bits right. the benzene sticking up, but it's non-polar, but it wasn't fitting into the hole. They recognized that had to get the correct orientation. After VR, where there are discussions on how do you think it worked, again, they discussed the importance of shape and electron density. Two examples of the discussions, Kyle and Craig would say both have different orientations. The receiver doesn't get, if the receiver doesn't get, it doesn't fit into the receiver. I would say that they need to fit electron density and electron pore and non-polar, they would need to fit into the pocket. So this goes, they come to the conclusion that there are 3 pockets, 3 bits need to fit in. And Dom made, again, similar sort of things. We have different parts of molecule. You have a neutral side chain, a positively charged region, negatively charged region, has to fit. Electron-rich region of the molecule to fit with the electrophilic region, which is electron-poor region, taste receptor, positively charged part. Nucleophilic part, the negative part, different enantiomers. They were using chemical terms to describe what was going on. Okay, so findings in this, initially students explained taste based on the concept of shape only. In the IVR, they recognize the importance of charge as well. Some students were not used to the 3D environment, so they really didn't explore all that much, even though this was their second activity. They focused on individual factors rather than talking about a holistic approach. The students used embodied, those who did use embodied actions and visual cues, they seem to gain a bit more, and they use it to confirm their ideas, particularly at the end when they're testing. Some of those students will put it in, take it out, and put both in a few times to see which would work best and why. I think we need to give a bit more opportunity to the students to explore and integrate multiple components and extend that thing. So that program, I think, can be extended a bit more. The IVR improves the students' understanding of molecular shape, electron density, and how that impacted on taste. And so I think the program seemed to work quite well. It delivered what we wanted, but I think we can extend it a bit more to challenge them to a greater extent. The last one, this is going to be very quick. What's the time? Oh, I think
yeah.
More, you want me to stop?
Yeah, 3 minutes. It's okay.
Okay, so yeah. I'll do this one fairly quickly, just to give you an idea of what we do, but then I'll jump through all the comments. Okay, the objective here was, this was actually the first one we developed. How do students explore a protein, and how can we use virtual reality to help protein interactions? So in this activity, the students would construct acetylcholine and the electron density map of acetylcholine. Then they will explore the enzyme that reacts with acetylcholine esterase, and they could visualize that in multiple ways. This is on the left-hand side, you see the electron density map. On the right-hand side, the ball and stick model. And then they would explore. So they would place the acetylcholine into the receptor, into the gorge as it enters the enzyme. And then having got that right, they then take it through and put it in the active site to trigger the reaction. And we analyze this by looking at, again, what the students were seeing but where they were standing. And we found that where they stand is important. So people like Ben and Maya had a very good approach, and they seemed to learn a lot in this process. And so we mapped it like this. So this is the reaction site, and that's the entrance to the cavity, and this is acetylcholine. And so what we did, we mapped it out. So what Ben and Maya did when they start, this is where they were, Ben and Maya, and the acetylcholine, this is the enzyme. They put it in site, they talk about it, they have discussions. Now, maybe this is right, we need to have this bit of red, because blue is interacting with red, so they move it over there, and then say, maybe we go this way, that's not right. Then Ben goes inside, checks what's inside, calls Maya to go inside, and they explore the inside of the cavity. They take the molecule in, see how it should fit inside the cavity, then they go back and place it on the outside. So this is how it's going to enter. So they have explored the whole area. They've moved around a lot. And our finding was that the people who move and explore to a greater extent seem to be learning to a greater extent. Okay, I'll jump through these fairly quickly. These are just some not detailed analysis, but overview from watching these activities. That the seeing the protein and some of the comments from the students, the enzyme was an abstract word without any concrete shape, and they appreciated that this is the first time they've seen an enzyme as a structure. Until then, it was the name on the top of an arrow. And they appreciate to be able to see the mechanism of the reaction in virtual reality. But they missed a lot of opportunities, particularly those who didn't explore. And they thought the most fun part was actually constructing the molecule in VR and dragging it into the active site. They commented on doing rather than observing, and they liked the fact that they were actually actionable components. Exploration and comparison depending on the familiarity of the different modes. Again, students who walked around a lot seemed to gain the most. I won't worry about the student comments in the interest of time, but their comments basically were saying they enjoyed it. The future directions, we hope to develop this. We're applying for more funding to extend these programs, and I can talk about those in discussion if you want. Summary of what I've said, in the interest of time, maybe I'll skip that, but I went through 4 studies that we've done so far, 2 with the snowflakes, 1 with taste and 1 with protein substrate, and we need to do more on those. Our conclusions and future directions, I think that immersive virtual reality has a lot to offer. It's still an expensive process and still very difficult to scale up for lots of people. But there are opportunities to have different versions that can be scaled to a classroom. And I'm happy to discuss that in the chat afterwards. And for our sake, we've learned a lot on how we should think about putting these programs together. And the next ones we develop, I think, will require less revision. Okay, there's some of the references I use, but I want to draw your attention to this YouTube channel. So if you go into YouTube and type in immersive chemistry visualization, you'll see a lot of the videos associated with what we are doing. And some of the activities I've talked about, you can see them not in virtual reality scape, but videos of them. And with that, I would like to say terima kasih, and oops, I've lost a misspelling here. The A has fallen off, sorry.
Yeah.
Terima kasih. Any questions?
Okay, thank you. Terima kasih, Prof. Moserino, for very, very insightful presentation. And then we just say that, yeah, this is wow, because the immersive virtuality a little bit far, yeah, that if some Indonesian would like to do, and hopefully we can learn more from you. Okay, please, everyone, if you want to ask directly to Professor Moserino, you just use the feature raise hand on your Zoom, and then after that I will read some questions also that already dropped in the chat box. Okay, please, I would like to give opportunity first to participant who would like to directly ask to Professor Moserino. Please raise your hand. Is there anyone here? Not yet.
There's a few in the chat.
Yes, there is one questions participant that would like to ask directly to you, Mauro. Yeah, please, Pak Wata.
Thank you very much, Prof. Moserino, for the nice presentation. Thank you, Dr. Nurma, for the time. Let me introduce myself. My name is Muhammad Waton, a teaching staff at Universitas 11 Maret. I'm also teaching the organic chemistry, and I found that your presentation really interesting, and then I'm really interested to like how to apply that the concept to explain the stereochemistry in the class. I was wondering, for the further development of the research, is it possible that the virtual reality is integrated with the computational chemistry, where you can to do simulation, how to perform like the synthesis of the compounds, and then because like you mentioned about the the correlation between the compounds and the receptor, the different stereochemistry will have different tastes. One is bitter, one is sweet. Another example is like thalidomide, where it's like morning sickness, where one effective medication and then one stereoisomer as the mutagenic isomers. I was wondering, like, the further development, if the virtual reality can be integrated with the computational chemistry. For example, if I'm standing in the laboratory, I can do virtual reality to do simulation about the compounds, and then I can directly found the biological activity, for example, a quantitative structure, activity, relationship. So once I got the result, I can do the synthesis in the laboratory. Is it that possible,
Yeah.
Professor Mauro? Thank you very much.
Okay. Yes.
Yeah,
Thank you, Dr. Waton. Okay, please, Mauro.
Thank you for your question. It's a complicated question. Couple of
Yes.
things. Yes, you can do some computer modeling, and there are many programs that will show docking of one molecule into a receptor site and will give you a number. And so the students can see that. And we found out even with that, when we were looking at the hydrogen bonding and the students using Odyssey, which is a good program for molecular modeling, and they were looking at hydrogen bonding, they could see that the effect of angle and shape, and the effect of angle and distance on the strength of the hydrogen bonding, and they could get numbers. But that didn't seem to carry through in the discussions afterwards. So they could get a number, and they'd write that number down, but having an understanding of how that plays in the effect is not necessarily there. Once you've got your knowledge of chemistry and my knowledge of chemistry, a computer simulation that you dock and it says, okay, this is the expected activity, we can translate that to something real. A student sees that as a number, and they may recognize that this is a bigger number or a smaller number, so that one's better than the other. But when they have the two molecules that they're moving into the shape, they are putting it in place. They are seeing it doesn't fit, or it does fit. I think the learning there is more powerful. And I suspect you can do it with a computer program. You can do some of these things with Odyssey, but they are not as tactile. The thing you can do in virtual reality is, if I want to pick up the molecule, I use my hand, I catch it, I move it, I put it in place. If I want to do that in a computer, I've got to learn how to move these things and zoom in, zoom out. I use that with some of my crystal structures. I use things like Mercury and Avogadro onto 2D screen, but I can see the images, and I've learned how to see them on the 2D screen. When I'm showing them to my students who are not so accustomed, they're often lost, and I have to slow it down and point out what I'm looking at. So virtual reality is a little bit harder to set up, but not that hard, in that with the protein structure, we just took the protein from the crystal data bank and used Unity to convert the coordinates into a virtual reality image that then they could play. So we didn't have to build it. We just used the crystal data bank CIF file, import that in, Unity then transforms that CIF file into a virtual reality activity. And from Unity, we can then see that protein, zoom in and out. We can see it in various forms because that information is built into that program. So it's not hard to take a crystal structure and turn it into a virtual reality object. And that's what we did with some of our compounds. We can do it on a computer simulation. We felt that that was not such a good learning experience, but not a bad learning experience, by the way. We were looking, our project was focused on how do we use virtual reality, but it's still a good learning experience, but it's a different learning experience. You know, yes, you can do it. We did do it. Roy Tasker, one of the guys on our research group, has done a lot of work with visualization using 2D screens and videos. And so there is a lot to be gained from that. And if the students are doing the docking, then they have to align these things. Yes, I think it can be done. We haven't done it. I just think that in some respects, once the program is there, the students being able to explore in virtual reality gives them a little bit deeper understanding of what's happening. Yeah. But the other one certainly works very well. It's worked very well with many other times. So I'm not trying to say it doesn't work. The disadvantage of virtual reality is it's very hard to do with a class, whereas a computer simulation, as you're talking about, is much easier to give to a class activity. So there are pros and cons. I see what you're suggesting is certainly a useful learning tool and useful learning activity.
Maybe the next project, Prawaton, next project collaboration, and then we try to develop it. Thank you very much, Mauro, for the answers. Thank you, Dr. Waton, for the questions.
Thank you for the question.
I'm going to go to the question in the chat box, Mauro. Here, one from Dr. Lina Mahardiani. She asks, she has two questions. The first question is how the sensory, action, social affect each other in immersive learning process. This is the first one. And then the second one, what is the feedback from the students learning about the experience using IVR? Yes.
Okay, so for the virtual reality, I mean, most people use virtual reality and focus on the sensory component because it's there to see things and it's very much a see. Some virtual reality activities will include some actional component and some have audio. We've had, we've seen some where the audio is not a lot more than mood music or to give them help block out the rest of the world. And in some respects that can be useful because if there's noise around, you're not immersed. So if you're going into an area where you are, for example, exploring an industrial site, having the sounds of an industry in your background helps you feel like you're there. Walking through an industry that's completely quiet may not have that same sort of thing. So you can use the sensory. The visual, I think most people understand, and that's what they're thinking about. But using sound can help a lot to help them feel like they're in that space. And with the actional, if you get them to do things, then that's part of helps them learn. They're not sitting in front of a screen, listening or watching something. They're moving around and they're picking things up. That component helps. Even with a plant, if you're doing a virtual reality of a plant, and so one of the things that virtual reality is often used for is being able to transport students to somewhere that you can't take them. And so if you want an industry, the chemical engineers are using this for site visits. They put this on and then they can effectively walk around the site. And so they are using action or standing in this point and then they're moving around looking to see observing various parts of the industry. So that's a key component. What did the students think? We asked the students most of them said this was great. No one said they felt sick, because one of the concerns often with virtual reality is motion sickness. None of them made any comment that they felt uncomfortable or sick on that process. And I think part of that reason is because in our programs, any movement was initiated by the person. So whereas a lot of the times when you put virtual reality on for those theme park type things, you're not moving, the roller coaster is moving or the airplane is moving, and that makes you sick. But if you're moving your head to see something, that's a natural movement, and it's natural, the scene changes naturally. And so none of them seem to have that. We also asked them how they felt about doing it in pairs, because they all did it in pairs. And everyone said that they preferred doing it in pairs. They liked having a partner. That partner helped them understand. The partner helped them discuss. And so that they felt that learning experience as a social activity was so powerful. It meant having a partner was good for learning, but in some respects not so good for us, because it tells us that we should not scale it up to have something that is an individual activity that everyone can put their headsets on and do by themselves. Because as soon as we make it so a program that they can load on their computer and put the headsets on and do it in their own time without a partner, they've lost that key component that all the students said is very important. So we're kind of stuck here, that we don't know how to make it more accessible without losing that student interaction that they've all said is very valuable.
Yeah. Yes. Thank you.
Nice question. I was thinking about that when I read it, and I thought,
okay, about the misconception. Yeah.
Thank you.
Yeah. Okay. Thank you, Dr. Dina.
Thank you.
Yes. Okay. And the next is questions from Professor Saputro. He asks possibilities, right? The possibilities using IVR to have a significantly reduced student misconception, especially in chemical bonding that we also read in some publication. Please, Mauro. Yeah.
This is a challenging question. Thank you very much. We were discussing with this, and have a colleague in Queensland who's exploring virtual reality to look at shapes of molecules and VSEPR and things like this. And it may be something we should think about for the next one. We pushed that away because it was a hard question to answer, but it's a question we need to address. I think it will help, because if we design our activity such that when the students are building their molecules, they can see, depending on what level we want, if we're looking at simple VSEPR type thing, see the impact of lone pairs of electrons on shape, and move them around and have it so that when it's in the right orientation, the color again is green, and when it's not in the right orientation, it's not green. And so we can use that to help them build how the bonding goes. Even possibly things like SP2 and SP3 for organic chemistry. One of the things I would really like to be able to teach, and I don't know how to do it yet, is use virtual reality to help them to recognize why a double bond is more reactive than a single bond. You know, a student would think, and quite naturally, a double bond is stronger, so it should be harder to react than a single bond. But if they understand, and we can help them see the pi bonds, then they can understand, because of the pi bonds, that's a much weaker bond. The double bond is not too not the two identical bonds. That's and so that's not clear way we draw things and way we describe things when we're speaking. We say double bond. We don't say pi and sigma bond. So the students think double bond are two single bonds, two sigma bonds, and using virtual reality to try and do that is a challenge. It's something we should be thinking about how to do. And because, understanding these misconceptions of bonding and the dynamic nature of bonding, but also just the orientation and geometry and how different bonds, they're not all the same. And that's something that's a challenge and not easy to do. But it's something we need to think about.
Yes.
I'm sorry, I can't give you much more of an answer there.
The next collaboration, hopefully, Prof. Saputro and Prof. Moserino.
Happy to talk about these things.
Okay, thank you
Hopefully
very much for your response, Prof. Moserino.
Hopefully next year when it's face to face, I can come there and spend time talking to people.
Hopefully.
Thank you very much.
Then, thank you, Prof. Saputro, for the questions. And this is the last questions, Mauro, from Farli Bondak, this from the Philippines. The question is about the other computer simulation that you use. Is this free, software free? Yeah.
Well, there are some things like Avogadro and Mercury, programs you can visualize molecules. They are free. I think you can buy a paid version as well, but I use the free version. And they also allow you to take a crystal structure from the crystal data bank and put that in. You can build your own molecules, but you can use a crystal structure and look at that. So if you have a CIF file from the crystal data bank, you can import that into Avogadro, and then that will show the structure, and you can rotate that around. And so there are a number of free visualization softwares. I've used Avogadro and Mercury, but there are others as well. I use a Mac, so a Macintosh has less programs available than a PC. So if you're on PC, then your opportunities are much greater.
Yes. Okay. Hopefully it has already answered your questions. Okay. Yes. Thank you, Mauro, for the answers. Now, because we are at the end of the session, the first binary session, that's very interesting to hear the three research of yours related to IVRs, and it's very insightful, some more knowledge and also fundamental things to do. You not only combine the things in a term of it's substantial, I mean the knowledge of the organic chemistry itself, but how the sensory, actional, narrative, social can be planned together to still have the activity for the students. You do it in pairs. The research also, you do it very details and nice finding. We would like to see more from your research. Thank you very much, Professor Mauro Moserino.
Thank you for the opportunity. It's been an absolute pleasure.
Yeah,
thank you.
We have it's a great honor to have you. And from the committee, as the appreciation, we would like to present the certificate of appreciation for Professor Mauro Moserino. Here they are.
Thank you.
Yes. Thank you very much, Prof. Moserino. Yes. Okay.
You're welcome.
That's the last of the session. Thank you for your coming. Hopefully the next collaboration will go further after this, Mauro. Yeah, I will contact you.
I have a question.
Yes.
If I can, because this is going for 2 days, can I listen in on other speakers?
Of course. Yes.
Yeah. Okay.
Yeah. Of course. We are very glad to have you if you want to do it in the 2 days.
Yeah. Certainly. I would like to hear some of the other speakers. And if I can, I will.
Yes, of course. You are invited, cordially invited.
Thank you very much. Thank you.
Thank you once again to Professor Mauro Moserino. That's the end of our first plenary session. Thank you for participants who already share the questions, and so we have already a nice discussion. And now I give back to you, Master of Ceremony, Camilla, and also Aji. Thank you very much. Good morning. See you next time.
Thank you very much. Thank you.
Thank you very much, Professor Marcelino, for insightful research and nice presentation. And also thank you for Dr. Nurma, who led our discussion session. And ladies and gentlemen, after this, we will have 10 minutes break. So to accompany our break, please enjoy our city, Surakarta.
Kangenku pada kota Solo rasanya semakin membuncah setiap kali mengingat sudut-sudut kenangan itu. Ya, kota di tepian Sungai Bengawan Solo ini memang mengesankan dan selalu mengundangku untuk menikmati setiap detiknya. Pagi, siang, sore, dan malam adalah waktu yang indah. Badai pasti berlalu. Ya, sepi ini pasti berlalu. Bayangkan, mengisi siang hari sembari belajar sejarah kita tentu menjadi pilihan pas. Museum Sangiranlah tempat untuk kita mengenal setiap zaman berkembangnya manusia dan lingkungan sekitarnya. Cukup setengah jam saja, kita tiba di Museum Sangiran. Jika ingin menikmati ketenangan, ke arah timurlah menuju lereng Gunung Lawu. Pesona Candi Suku akan membawa kita pada rasa ayem. Segarnya udara pun menambah sejuk suasana hati untuk sejenak melupakan kepenatan. Tak sampai 5 menit dari Candi Suku, alam menyuguhkan ketenangan pula. Ya, Telaga Madirdo. Memandang tenangnya air telaga, rasanya mata ini tak ingin pulang. Semilir anginnya pun seperti berbisik ramah, hingga raga serasa turut terbang bersamanya. Kota ini memang selalu memanjakan tamunya. Selain keramahan dan keindahan, makanan pun akan selalu menggoda lidah dengan berbagai pilihannya. Tapi sekarang masih sepi. Kita bayangkan saja yuk. Sate buntel kambing dan berbagai olahan daging hingga sumsum kambing tentu bukan hal mudah untuk menolaknya. Segarnya selat Solo juga sangat menggoda. Setiap cecap lidah pasti memberi sensasi segar ke seluruh tubuh. Seperti, sulit terucap. Ada makanan khas kota Solo yang tak lekang zaman. Sate kere atau sate jerohan sapi. Kini tak hanya jerohan saja, tapi juga dagingnya. Memang pada zaman dahulu, sate kere adalah makanan untuk masyarakat kelas bawah karena hanya berisi jerohan sapi. Sedangkan daging sapi untuk kalangan ningrat dan kelas atas lainnya. Ada satu lokasi untuk kita memilih berbagai makanan di kota Solo. Galabo. Layaknya etalase, makanan-makanan kondang di kota Solo akan mengajak kita menikmati nuansa malam di pusat kota Solo. Tak hanya Galabo, di Solo juga ada sentra kuliner lainnya, yaitu kawasan kuliner Kota Barat. Jangan lupa rasakan gurihnya serabi saat kita di kota Solo. Kapan lagi? Iya, aku tahu itu semua tak mungkin sekarang. Tunggu sampai pandemi COVID-19 berlalu. Ada beberapa pintu gerbang untuk memasuki kota Solo. Naik pesawat kini tak hanya penerbangan dari Jakarta loh. Jika menggunakan kereta api dari Jakarta, Bandung, Surabaya, dan kota lainnya terasa nyaman juga kok. Naik bis pun ada banyak pilihan. Kalau mau menggunakan kendaraan pribadi, melewati tol Trans Jawa akan menghemat waktu tempuh Anda. Setibanya di kota Solo, ribuan kamar hotel siap menanti Anda. Tentu saja nyaman. Nah, mumpung lagi work from home, kita rencanakan liburan ke Solo yuk. Jadi, jika nanti keadaan membaik, kita bareng-bareng dolan ke Solo. Ayo ke Solo.
Kota Surakarta atau Kota Solo adalah kota dengan segudang daya tarik untuk menjadi pilihan kunjungan Anda. Dengan potensi kekayaan seni dan budayanya, tentu saja Kota Solo menjadi pilihan tepat bagi Anda untuk berwisata. Selain itu, Kota Solo terus berbenah untuk menjadi kota meeting, insentif, convention, exhibition, MICE. Nah, di Kota Solo, Anda tak hanya dapat menggelar pertemuan di gedung-gedung pertemuan saja. Saat ini pemerintah Kota Surakarta telah menyediakan bis dengan desain khusus sehingga dapat menjadi tempat meeting yang nyaman. Gatot Kaca Meeting Bus menyediakan berbagai fasilitas untuk kenyamanan meeting Anda sembari menyusuri jalanan Kota Solo. Bis berkapasitas 15 orang ini menawarkan pengalaman berbeda untuk meeting Anda. Sebagai kota jasa wisata, di kota Solo Anda dapat menemukan tempat-tempat wisata dengan berbagai warna. Mengunjungi Lokananta tentu menjadi destinasi menarik saat berada di
Okay, thank you to all participants. The break is already over. And for the next session, ladies and gentlemen, is presentation from our second keynote speaker, Dr. Sri Mulyani from Universitas 11 Maret Surakarta, Indonesia, led by Lina Mahardiani, PhD from Universitas 11 Maret as a moderator. Before we start the presentation session, I would like to introduce our moderator, Dr. Lina. Please. Dr. Lina is a lecturer from Chemistry Education Department, 11 Maret University. Dr. Lina area of expertise is physical chemistry. Without further ado, let us welcome our moderator, Dr. Lina Mahardiani.
Ladies and gentlemen, allow me to be your moderator for the second session. I will introduce the next presenter or keynote speaker, Dr. Sri Mulyani. Dr. Sri Mulyani.
Excuse me, Dr. Lina, your voice is too small here.
Can you hear me? Yes. Okay, thank you. Okay, so I would like to introduce you to the next speaker, Dr. Sri Mulyani. She's the head of the Department of Chemistry Education. Her expertise is biochemistry and also chemical education. And today she's going to give a talk on biochemistry. Dr. Sri Mulyani, you have 1 hour with the question and answer. So Dr. Mulyani, the time is yours. Okay, thank you, Mr. Lina. Right. So I show my presentation here. Okay, I'm sorry. Can you see my slide? Yes, perfectly. Okay, and can hear also my voice, yeah? Yes. Okay, thank you. Thank you, Ms. Lina, for the times and the Honorable Professor Moro. Thank you. And also the participant in here. Good morning. Now I want to present my slide entitled the non-ribosomal peptide synthetaser. In halometabolite biosynthesis, yeah, and the subtitle is what is the role of the thioesterase. Okay, I hope my explanation can be understand for you. Yeah, so I have prepared my slide full full with letter. Yeah. Okay. So in this presentation, I want to give some description about the halometabolite and also glycopeptide and non-ribosomal peptide synthetase, non-ribosomal peptide for the synthesis using dogma central, and polymyxin biosynthesis, thioesterase, and the role of the thioesterase. Okay. The halogenate natural compound have been known for many years, I think, and nowadays over 3,500 different natural organoleptons are known. Yeah. And we know the halogenate organic compounds are widely used, for example, for pharmacy, herbicide, yeah, fungicide, and insecticide, flame retardant, intermediate in organic synthesis, solvent, and so on. Some of these halogenate metabolites have great importance as, for example, antibiotics such as vancomycin, polymyxin, pyrrolidine, or pentachlorobenzidine. These the structure, the molecular structure of the vancomycin, polymyxin, pyrrolidine, and pentachlorobenzidine. Non-ribosomal peptide. This is one of the example of the halogenate organic compound. Yeah, and this is also a class of peptide secondary metabolite usually produced by microorganisms like bacteria and fungi. And also the peptide are not synthesized by ribosome, yeah, but using the non-ribosomal peptide synthetase. This the name of the complex enzyme synthesized non-ribosomal peptide synthetase. This is also extremely broad range in biological activities and pharmacological properties. And the non-ribosomal peptide antibiotic, cytostatic, and immunosuppressant are commercial use. And then now we will focus on glycopeptide antibiotic. This is, for example, the glycopeptide antibiotic of the vancomycin type. Yeah, for example, the ones is polymyxin, vancomycin, chloroaromamycin, and teicoplanin. When we look at the main of structure, yeah, these vancomycin types is consist of 7 amino acid, yeah, non-proteinogenic amino acid. This is the ones. Number 2, this is the backbone of the peptide. Yeah. This is the number amino acid number 1, number 2, number 3, number 4, number 5, number 6, and number 7. Yeah. This also contains this is a find ring. Yeah. A, B, C, D, E. Yeah. Okay. So this non-ribosomal peptide, yeah, non-ribosomal peptide is synthesized, yeah, by the non-ribosomal peptide synthetase. What is the non-ribosomal peptide synthetase? Non-ribosomal peptide synthetase is a set of the module, yeah, each of which contain all enzymatic activities to incorporate one amino acid constituent into the product. For example, the type of the vancomycin antibiotic contains of 7 amino acid, yeah, and the order and number of the module generally determine the sequence and length of the peptide produced. The module can be subdivided into different domains responsible for the single chemical reactions. So normally in the non-ribosomal peptide synthetaser contains initiation modules, elongation modules, and termination modules. The initiation modules normally typically as D domain, consists of adenylation domain and PGP. PGP is a peptidyl carrier protein, and for the elongation modules is 3 domains, contain 3 domains. This is C is condensations, A adenylations, and P PCP, peptidyl carrier protein, as thiolation. And then for the terminations, normally as tetradomain, consists of C, and then E adenylation, PCP, and one is thioesterase. Okay, so this is to describe the assembly line of the non-ribosomal peptide synthetaser. This is the initiation module. One module contains some minimal 2 domains. And then this is elongation module, and the third is termination module. So when we, for example, to synthesize this peptide, first the initiation module consists of adenylation module and thiolation domain with PGP. And the second elongation module built and termination condensation domain and an adenylation and the thiolation domains also. And for example, when we start to the synthesize, first in initiation module, the A domain will recognize and activate the amino acid substrate. This is amino acid substrate into the form on the acyl adenylene covalent bond to hollow PCP. This is the PCP. Connect to the phosphopantothene here, and the corner is sulfitryl to tie the amino acid. And then the domain C, catalyze amide bond formations between the downstream amino acid substrate and the upstream amino acid to growing the peptide chains here. And then the domain D, PGP, will release the full-length peptidyl chains from the covalent attachment to the most downstream PGP domain by, for example, hydrolyze or cyclization, or sometimes also as a specific transfer to a functional group. Okay, Okay, when, for example, this one, when we have 3 amino acid in this peptide, this one, first is amino acid 1, and then the acyl group incorporate to the PCP this one, and then the third, and when we complete is, and then the thioesterase will release this peptide. So when we compare with the ribosomal peptide synthetaser, when for example here, this is to synthesize the proteinogenic peptide. When we see in here, for example. Okay. So you can see here, this is involves the ribosome, when the non-ribosomal peptides is without ribosome. For example, in the here initiations, yeah, there are small unit ribosome, and this is the messenger RNA. Yeah. Now the amino acid one, yeah, and then the large subunit of ribosome, yeah. So this is to make a complex initiation, yeah. And then the next two elongations, this codon, yeah, suitable with the anticodon, yeah, the anticodon suitable will bring this amino acid and then to tied to the amino acid first here. So yeah, the next steps, formation of the peptide bond between the amino acid, methionine and proline. And then the next, yeah, this is for the, for example, the explanation about the formation of the bond. And the next, so when we next codon, yeah, with the amino acid asparagine and then glutamine, and the last, yeah, for terminations, this is a release factor will release this amino acid, yeah. So this synthesize peptide using this ribosome, yeah. So when we compare between the NRPS and RPS, yeah, the NRPS produce usually a shorter peptide and can contain some non-protein organic amino acid. And in NRPS, the assembly of the amino acid into the peptide is facilitated by the cofactor phosphopantothene of the multi-enzyme complex through alternate transpeptidase and transteolase reactions in a similar way in the fatty acid biosynthesis also. Yeah, but in ribosomal peptide synthesis here, a peptide formed in the ribosomal peptide synthesis is a result of the sequence process of the replications, transcriptions, and translation of the Greek central dogma. For the NRPS, yeah, this is not by RNA, yeah, but by the NRPS. And the next transteolase in NRPS is analog to translocation in ribosomal chains elongation. The other hand, yeah, polycated synthase. Polycated synthase is also as enzyme complex that produce polycated, yeah, when non-ribosomal peptide synthase produce non-ribosomal peptide, and when polycated synthase produce polyketide. The PKS is closely parallel to that fatty acid synthase, and the both PKS, polycated synthase, and fatty acid synthase convert short chains acyl-ASCoA, yeah, acyl-ASCoA thioesterase into long acyl chains product by a series interactive elongations cycle that add two carbon unit, for example, for fatty acid synthase, and also for polycated synthase. Okay. There are multiple domains or the subunit that participate in specific chain initiations, yeah, and elongation in termination step. This is, for example, the organization of the fatty acid synthase. This fatty acid synthase consists of 6 enzymes. Yeah, the first is ketoacyl ACP synthase and malonyl CoA ACP transferase, acetyl-CoA ACP transatylase, anenyl ACP reductase, yeah, the ER is anenyl ACP reductase. Here is alpha ketoacyl ACP reductase. HG is hydroxyacyl ACP dehydratase. So this enzyme system fatty acid synthase complex, yeah, is the peak in a cycle consisting of 6 enzymatic activities, and ACP is located at the center here. Yeah, the enzymes shown in the blue are active in the next step. For example, here. Yeah, and when we in fatty acid synthase, yeah, the first this is precursor is acyl-CoA. Yeah, the acyl, yeah, activated with S-CoA, yeah, S-acetyl-CoA, and then tied into the suvitril, yeah, in S half of the HEP. When non-ribosomal peptide synthetase, we use PCP, yeah, for the fatty acid synthase, and polycated synthase, we use ACP, acyl carrier protein, yeah, and when PCP is peptidyl carrier protein. So after this acyl tied into this pantothecin of the HEP, and then from this one, yeah, the malonyl, yeah, the acyl incorporate into the ketoacyl ACP synthase, and then the second, the donor acyl, yeah, as malonyl-CoA incorporate into the ACP, and then this acyl from the ACP incorporate to the acyl in keto acyl synthase, yeah. So this is condensate into 4C, yeah, 1, 2, 3, 4, yeah. This is as ketobutyryl ACP, yeah, and then this ketobutyryl ACP with 3 reactions, yeah, to become this, yeah, butyryl ACP, yeah, and then as butyryl ACP as the second precursor, yeah, the second cyclus, yeah, and then this is to tie into the keto synthase, yeah. So this is one cyclus, yeah, one cyclus to elongate 2C, yeah, from 2C applies to C, and then to become 4C, yeah, 4C. This is as butyryl. So, and the next, yeah, we can continue the second cycle and triple cycle and the fourth cycle. So until for the fatty acid synthase until 16 C, ya. Jadi C, for example, for the palmitoyl acid, ya. Okay. So for the polycated synthase, yeah, this is similar, I think, but the polycated synthase can use the acyl-CoA, malonyl-CoA, malonamyl-CoA, propionyl-CoA, butyryl-CoA, cyclohexyl-CoA, benzoyl-CoA, hydroxy 5-amino-benzoyl-CoA, malonyl-CoA, and methyl-malonyl-CoA also as precursor. Yeah. So these ACP, these polycated synthase, there are 3 types. Yeah, the type 1. This is the A. This is type 1 is very large, yeah, highly modular protein. The domain are gathered in cheese and parts large, yeah, and also as multi-domain subunit, yeah. And the 4 PKS type 2, yeah, are aggregate of the monofunctional protein. So, but for the PKS type 3, do not use ACP domain, yeah. But for the PKS type 1 and PKS type 2, use ACP domain, yeah. So this also, yeah, like for the fatty acid, AT in PKS is acyl transferase, GR is ketoreductase, GS is ketosintase, DH is dehydratase. Yeah. Okay. This is this description of the ACP, acyl carrier protein. Yeah, consists of the serine side chains and 4 phosphopantothene and also pantothenic acid. Yeah, and then this sulfitryl group, yeah, used for tailoring of the substrate. So we will to the next description about the polymyxin biosynthesis. This is one of the glycopeptide of vancomycin type. Yeah. First is solid by Nadkarni. Yeah, and also consists of 7 amino acid residue, amino acid ones like for vancomycin, teicoplanin, and also chloroaromimycin. Yeah, the 7 amino acid residue is N-methyl leucine. Yeah, the one, and the third chloro-beta hydroxytyrosine. Yeah, and the third is asparagine. The fourth is beta hydroxyphenylglycine. Yeah, and the fifth is 4-hydroxyphenylglycine, 3-chloro-beta hydroxytyrosine, and the seventh 3.5 dihydroxyphenylglycine. So the biosynthesis chain cluster of the polymyxin consists of 14 ORF, yeah, and we have identified the ORF. One of these ORF is, for example, this PHP, yeah, the PHP, the function as thioesterase, and we will discuss in the next, yeah. So the organization of the polymyxin biosynthesis chain cluster have identified, yeah, the name, and then from plus, yeah, we can determine, yeah, the functions, and some of them have been also proved by in vitro. Yeah. So this can involve in the polymyxin biosynthesis chain cluster. For example, here, yeah, this the non-ribosomal peptide synthetase, yeah, consists of, for example, this one module, yeah, PPSA, module PPS BA, no, that is non-ribosomal peptides, yeah. This is the initiation module, yeah, and this elongation module, yeah, and then this termination module. For example, this module 1, yeah, produce the amino acid leucines. Module 2, chlorohydroxytyrosine, yeah, and then the module 3 asparagine, yeah. This is from the thiolase, and then the condensation, the leucines condensate with chlorohydroxytyrosine, yeah, into dipeptide, yeah, and then with asparagine to tripeptide. So the next non-ribosomal peptide synthetase, this is PPSP, and then the third is PPSC. Yeah, okay. This chain, yeah, in the cluster, and then cooperations, yeah, to produce these 7 heptapeptide, yeah, the heptapeptide, yeah. And then the last is thioesterase, yeah. Now this thioesterase we will discuss, yeah, in the next, yeah. We'll release this heptapeptide, yeah, and then facilitate also to the next reactions, for example, cyclizations, yeah, and then also incorporation for the other group, for example, these halogenate, yeah, because in polymyxin consists also the chlore, yeah. Okay, this one of the PHP, yeah, we have crystallized, yeah, and characterization also, and these PHP the function as thioester, yeah, thioesterase release these tyrosine, yeah, this is beta hydroxytyrosine to beta hydroxytyrosine. This is the beta hydroxytyrosine that with the SNAC. SNAC is mimic with the phosphopantothecin, yeah. And then when we study in vitro, yeah, we use this SNAC as phosphopantothecin. So this, I think this is a prediction function. I have explained the order of the reactions. The next we will discuss about the thioesterase domain in the glycopeptide antibiotic biosynthesis. For example, for the teicoplanin and vancomycin, this is the aglycon maturations, yeah, and the non-ribosomal peptide synthetase here consists of 1, 2, 3, 4, yeah. Teicoplanin 9, teicoplanin 10, teicoplanin 11, and teicoplanin 12, yeah. And after these heptapeptide compose here, and then the other enzyme, for example, oxy-A and oxy-C, yeah, this is oxidized and make the ether here is, yeah. So, and this involves the teicoplanin 12 module, yeah. This module consists of condensations, adenylations, thioextraction, and X, yeah, X. So the we will discuss about the thioesteration function in here. Yeah. So this thioesterase, we know about 2 thioesterase. Yeah. The first is thioesterase type 1. Yeah. Typical the thioesterase type 1 is a concept structure and appeal from the recent structural characterization and complete non-ribosomal peptide synthetase module to also display a degree of flexibility in their conformations relative to the rest of the catalytic machinery. And the TA domain rely upon the 2-step mechanism to free peptides from the non-ribosomal peptide assembly line. In the first step, the carrier protein found intermediate in is loaded into the concept serine, yeah, serine of the PCP, and the in this point, yeah, the TA bond intermediate can vary substantially depending on the nature of the intercepting of the nucleophile. So for the TA domain from the teicoplanin non-ribosomal peptide synthetase displays a clear preference for the correct cross-linking state of the PCP bond peptide, and the TE domain activity relies upon the retention of the extended and terminal linker found within the final non-ribosomal peptide synthetase module. Once more, highlight the impression of the ability of the TE domains is to act as crucial logic gate that maintain tight control over non-ribosomal peptide synthetase biosynthesis. Yeah, when the late states, for example, yeah, of the peptide modification are required, for example, is prior to release, yeah, of the final, yeah, as a bioactive non-ribosomal peptide. And for the thioesterase 2 type 2, yeah, this normally, yeah, stress the fact that they are not covalently bound in the multi-enzyme, yeah. So this is the opposite of the TE domain. When the TE domain type 1s normally is covalent bonds in the multi-enzyme, yeah. And the thioesterase 2 thioesterase type 2 is most case not essential for the synthesis of the corresponding synthetase product, but they play an important role in the maintenance of the efficiency of the assembly line. And the role of the TE2 sometimes involves also the polypeptide and non-ribosomal peptide biosynthesis, yeah, is reviewed an implication for the combinatorial synthesis in the biology approach, yeah. And when we, for example, the role of the thioesterase type, yeah, forms some researchers have explained about the 5 functions, yeah. The first, this thioesterase can also correct the decarboxylate condensation. Normally, when the normal polycated chains elongation start with the decarboxylative condensation catalyzed by the ketosyntase domains, yeah. When the decarboxylation is incorrect, yeah, this thioesterase can give rise an acyl residue attached to the HEP, and then this thioesterase 2 hydrolyze, yeah, to edit this the acyl residue and leave the HEP free to accept a new decarboxylate extender unit transferred by the adenylate thiolase domain. Yeah, this is for example here. When this is incorrect, yeah, and then can to extend it here. Okay, for the second functions, priming the carrier domain, yeah, the ACP or PCP domains, yeah, are primed with a cofactor phosphopantothioneins transferase here, yeah, and then from the coenzyme A, the phosphopantothionein can also accept the acyl coenzyme A as a substrate and misprime sets inaccessible for an extended unit, yeah. Okay, so this hydrolyze, yeah, this thioesterase type 2, yeah, will edit, yeah, by hydrolyze the acyl residue and leave the carrier domain free to accept a correct substrate. So the next functions can also control of the starter unit, yeah. Okay, for example, when in the initial step, yeah, the adenylations and thiolases, yeah, when the starter unit corrects, yeah, can continue, yeah, this. So the residue is not cleave become a starter unit for the polycated chains when this is not correct, yeah. So and the fourth, as intermediate removal, the thioesterase type 2 can remove also the amino acid and polycated synthesis intermediate, including correct decarboxylate extended unit, if they are not readily processed by the downstream domains. And the last, can also providing intermediate produce release. This is the real function of the thioesterase type 2. This thioesterase type 2 specific for the certain moiety which are required for the construction of the full structure of the metabolite, release them from a specific carrier to make them available for the next biosynthetic step. Some thioesterase 2 release the complete PKS, polycated synthase or non-ribosomal peptide synthase product, as polycated or as peptide, from the multi-enzyme synthesis here. Okay. So how to proving the function of the thioesterase in vitro? For example, we have work in the thioesterase in the polymyxin biosynthesis. The first thioesterase, the name as BHB. BHB has been also predicted as a thioesterase domain that utilize the thioesterase bond of the putative okay. 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 We repeat again. The BHB has been also predicted as a thioesterase domain that hydrolyzes the thioesterase bond of the putative beta hydroxy tyrosine S PCP PPSD. PPSD is the second enzymes, downstream from the BHB when we refer to the organization of the polymyxin biosynthetic chain cluster. So, and then the putative beta hydroxytyrosine complex of the putative beta hydroxytyrosine SPCP PPSD, with the thioesterase enzymes, to release the free beta hydroxytyrosine. As mentioned previously, nicomycin P2 is similar also to freestanding type 2 thioesterase found in the polyketide synthase cluster and release free beta hydroxyhistidine from the thioesterase linkage of the 4-phosphopatotein prosthetic group. Analogy with these enzymes, we propose this PHP also have similar functions, with NICP2. So for proving the functions of the thioesterase, we synthesize the N-acetylcysteamine, that have mimic the terminal part of the phosphopantotein, so that we can amino acid F pantotein P PCP domain, can be we replace by amino acid SNAC for the proving by in vitro. So in analogy for this, it has been planned also to characterize the function of the PHP in vitro using beta hydroxytyrosine SNAC as a substrate instead the proposed natural substrate of the beta hydroxytyrosine SPGP PPSD complex. This is the figure of the amino acyl span PPGP domain. This is the acyl amino acyl group, and this is the pantoteinyl. And then we use this SNAC, the terminal part of the phosphopantotenyl, similar to the SNAC. So we use this terminal part, to replace the function of the phosphopantotheniol. So, and we have synthesized the amino acid SNAC, yeah, and we can prove also the function of the PHP of the polymyxin pure synthesis chain cluster as the thioesterase. So this is one of example to prove in vitro the function of the thioesterase. Yeah, and for this we should also synthesize the substrate. Yeah, because we cannot purchase this the substrate in market. Yeah, and we have synthesized the beta hydroxytyrosine from para-pensyl oxypensaldehyde. Yeah, this is the schema of the reactions. Yeah, and then the beta hydroxytyrosines. Yeah, we react with N-acetyl cysteamine. Yeah, and then the product is beta hydroxytyrosine SNAC. So, and the beta hydroxytyrosine, yeah, we have also synthesized, yeah, we with the precursor para-pensyl oxypensaldehyde. So that is to prove the function of the complex enzyme, yeah, in the chain cluster, yeah, to know the function in vitro. Yeah. So I think these all my presentations, and this is my reference use in my presentations. Okay, thank you for your attention. At the times, I gave back to the Miss Lina. Thank you.
Thank you, Dr. Mulyani, for your nice but complicated subject. So I would like to invite all the participants, if you have questions to Dr. Sri Mulyani, you may raise your hand or you may write in the chat box.
No one.
Okay, Dr. Hisbulwaton, please.
Thank you very much, Dr. Lina. Thank you very much, Dr. Simuliani, for a nice presentation. I know that research in biochemistry is challenging. Yeah, it needs requires high motivation and determination to do the research. As it is mentioned, it's a bit complicated for some. I was wondering, when you were doing research in developing, I'm sorry, to find the function of thioesterase for the compound of amino acid phosphopantotheniol. From the previous speaker, we talked about the stereochemistry. Do you also found in your research, the relationship, the stereochemistry of your compound and also the activity of that compound, whether one is active, one is non-active?
Yes, yeah, because we have discussed, yeah. Okay, we have synthesized, yeah, these beta hydroxytyrosines, yeah, but these beta hydroxytyrosines synthesis products have what is enantiomer, yeah. So these enantiomer, yeah, once we don't know, because we cannot spirit these enantiomer pair, yeah. When we use these preparative HPLC, yeah, it seen also one peak, yeah. But when we use this analytical HPLC, yeah, we found two peak, yeah, two peak. So we decide with this compound is enantiomer, but we cannot separate it. Okay. My colleagues also in Tübingen, yeah, with my my receipt for the synthesis of the beta-hydroxytyrosine SNAC, as also made and found, yeah, and he seeks this product to me, yeah, and then I prove the my activity of my enzyme using this substrate, yeah. This appears not active, yeah, with this. I'm sorry, I can prepare this a slide, yeah, but I want only to explain, yeah. For example, when my my product, my substrate, yeah, my synthesized substrate have to peak, yeah. When we separate in analytical HPLC, the peak ones, yeah, the peak one. For example, I give the A names, yeah, and the peak 2 is B, yeah. My substrate, the peak B is higher than the peak E. The enantiomer, what is this? Yeah, this enantiomer, yeah. This substrate ones, for example, or I mentioned as substrate E, yeah, and substrate B, yeah, the mix of the substrate A and substrate B. My synthesize, the substrate B is dominant, yeah, and my substrate from my colleagues in from Tübingen, the substrate E is dominant. So when I use my substrate, yeah, my substrate B, the activity is appear, yeah, the beta-hydroxytyrosines I can found in the HPLP analytical, but when we use the substrate E from Tübingen, yeah, this product, yeah, this product is beta-hydroxy, yeah, amino acid, yeah, okay. Okay, I can repeat my explanation, yeah. My substrate is beta-hydroxytyrosine SNAC, yeah. So when this thioesterase hydrolyze the beta-hydroxytyrosine SNAC, the product is beta-hydroxytyrosine. It's clear? Okay. So when we use my substrate, yeah, this product B dominant, we can find the beta-hydroxytyrosine, yeah, in the analytical HPLC. But when we use the substrate that substrate A dominant, we cannot found. So this is yeah, we have excited, yeah, because the first is, I think this is as competitive, yeah, competitive inhibitions. So when we check the kinetic, and then it is proof, yeah, when the one substrate is as inhibitor, yeah, and the other substrate is as substrate, yeah. So I have for a long time, yeah, to analyze, and for the with these results, yeah, we have excited actually. That is.
Thank you very much,
okay.
Dr. Sri Mulyani.
Okay.
Okay, thank you, Dr. Waton, for the questions, and thank you so much, Dr. Mulyani, for your feedback. And we still have 7 minutes before we end our second session. Okay, Dr. Sri Ratno, please.
Okay, thank you very much, Dr. Lina.
You can also in Indonesian.
Mrs. Mulyani, your presentation is very
Yes.
excellent. My question is very simple. What are the application your research in the industrial field and in daily life? Thank you.
Okay, the application in industrial field and in daily life, yeah, because we study about the metabolism, yeah, metabolism. For example, we study about the how the antibiotic is composed in the bacteria, yeah. When we know, yeah, the order or the reactions, yeah, to produce the antibiotic, yeah, when, for example, problems, for example, for the vancomycin, yeah, there are also apa namanya, resistensi, ya, for the resistensi, ya. World has known the resistant, for example, the vancomycin resistant Staphylococcus aureus, for example, VSRA, and also GISA, yeah, and also methicillin resistant of Staphylococcus aureus. Okay, by this study, when we know the biosynthesis, yeah, of these antibiotic in the microorganism, we can use this knowledge, yeah, to, for example, when we want to produce the similar antibiotic, ya, to apa ya, istilahnya untuk mengganti, ya, mengganti antibiotik yang sudah apa istilahnya di mana mikroorganisme itu sudah resisten terhadap antibiotik itu. Oke, ya. Oke, I think that is my explanations, ya, and saya kira itu sangat berarti karena kalau maaf saya jadi bahasanya, ya, karena kalau misalnya kita apa namanya tidak punya obat untuk mengobati suatu penyakit yang sudah resisten, ya, maka itu menjadi satu seperti sekarang COVID misalnya, ya, nih, ya, tapi ini adalah nih, this is the other microorganism, ya, this is a bacteria, and when COVID is virus. Okay, it's enough.
Okay, thank you, Mrs. Mulyani. It's very good research. Thank you, Dr. Lina.
Okay, thank you, Dr. Retno and Dr. Mulyani. Because the time is up, I will conclude that your Dr. Mulyani research, I believe that there's a lot of work to be done more.
Yeah,
so
a lot of stress also, ma'am.
Okay. So to perfectly synthesize the substance so that it can create or synthesize the substance that can replace the or outcome the bacteria that already resistant. Okay, thank you, Dr. Mulyani. And
you're welcome.
Aji, I will give it back to you.
Thank you, Doctor. Thank you, Dr. Mulyani and Dr. Lina, for the inspiring and insightful research and presentation as well as discussions. Ladies and gentlemen, we will now have a break until 1 p.m. of Indonesian Western Time. To accompany our break, please enjoy our beautiful city of Surakarta via video. Thank you very much.
tak hanya dapat menggelar pertemuan di gedung-gedung pertemuan saja. Saat ini pemerintah Kota Surakarta telah menyediakan bis dengan desain khusus sehingga dapat menjadi tempat meeting yang nyaman. Gatot Kaca Meeting Bus menyediakan berbagai fasilitas untuk kenyamanan meeting Anda sembari menyusuri jalanan Kota Solo. Bis berkapasitas 15 orang ini menawarkan pengalaman berbeda untuk meeting Anda. Sebagai kota jasa wisata, di Kota Solo ada seolah memanjakan imaji Anda pada romantisme masa lalu. Berdiri sejak tahun 1956, Lokananta adalah perusahaan di Lokananta tersimpan ribuan keping piringan hitam berisi rekaman lagu para pesohor bersuara emas seperti Waljina, Gesang, Titik Puspa, Din Slamet, dan Sam Saimu. Selain lagu-lagu, tersimpan pula piringan hitam berisi pidato-pidato kenegaraan Presiden pertama Republik Indonesia, Soekarno. Berada di jantung kota Solo, Museum Keris dapat menjadi pilihan berwisata dan mengenal salah satu kekayaan tanah air. Ribuan bilah keris mengenang kisah kepahlawanan di masa lalu. Kembarnya Gusti Raden Ayu Partini dan Gusti Raden Ayu Partinah. Taman Balai Kambang terbagi dalam dua bagian dengan fungsi sebagai paru-paru kota dan resapan kota. Hutan Partinah Bosch dan Taman Air Partini Twin, nama kedua area tersebut. Taman Balai Kambang berdiri sejak tahun 1921 dengan memadukan konsep Jawa dan Eropa. Predikat kota paling layak huni menjadi kebanggaan bagi kota Solo. Pemerintah Kota Surakarta pun terus berupaya menata dan melengkapi fasilitas kota agar semakin nyaman untuk tinggal. Salah satunya adalah pendirian Taman Cerdas di beberapa lokasi. Taman Cerdas menjadi tempat untuk belajar berbagai hal, mulai dari ilmu pengetahuan, seni dan budaya, serta pengetahuan umum.
Dan satu buah lagu saya persembahkan berhubung kita di Kota Solo tercinta, spesial untuk Anda semua, Kota Solo.
Kota Surakarta atau Kota Solo adalah kota dengan segudang daya tarik untuk menjadi pilihan kunjungan Anda. Dengan potensi kekayaan seni dan budayanya, tentu saja Kota Solo menjadi pilihan tepat bagi Anda untuk berwisata. Selain itu, Kota Solo terus berbenah untuk menjadi kota meeting, insentif, convention, exhibition, MICE. Nah, di Kota Solo Anda tak hanya dapat menggelar pertemuan di gedung-gedung pertemuan saja. Saat ini pemerintah Kota Surakarta telah menyediakan bis dengan desain khusus sehingga dapat menjadi tempat meeting yang nyaman. Gatot Kaca Meeting Bus menyediakan berbagai fasilitas untuk kenyamanan meeting Anda sembari menyusuri jalanan Kota Solo. Bis berkapasitas 15 orang ini menawarkan pengalaman berbeda untuk meeting Anda. Sebagai kota jasa wisata, di Kota Solo Anda dapat menemukan tempat-tempat wisata dengan berbagai warna. Mengunjungi Lokananta tentu menjadi destinasi menarik saat berada di Kota Solo. Menjelajah setiap sudut Lokananta seolah memanjakan imaji Anda pada romantisme masa lalu, jagat hiburan Nusantara. Berdiri sejak tahun 1956, Lokananta adalah perusahaan rekaman musik pertama dan satu-satunya milik negara. Di Lokananta tersimpan ribuan keping piringan hitam berisi rekaman lagu para pesohor bersuara emas seperti Waljinah, Gesang, Titik Puspa, Bing Slamet, dan Sam Saimun. Selain lagu-lagu, tersimpan pula piringan hitam berisi pidato-pidato kenegaraan Presiden pertama Republik Indonesia, Soekarno. Berada di jantung Kota Solo, Museum Keris dapat menjadi pilihan berwisata dan mengenal salah satu kekayaan tanah air. Ribuan bilah keris dari berbagai daerah dan berbagai zaman seolah mengajak Anda untuk memutar waktu, mengenang kisah kepahlawanan di masa lalu. Di Museum Keris Anda juga dapat mengetahui bagaimana proses pembuatan keris. Diorama dan informasi detail memudahkan Anda untuk mengetahui proses tak sederhana terciptanya sebilah keris. Tak hanya kekuatan raga saja, namun juga olah rasa menjadi roh penciptaan keris. Kota Solo juga tersohor sebagai kota kuliner. Salah satu pilihan kulinernya adalah tumpeng nasi kuning. Ya, makanan berbahan dasar beras ini menjadi sajian warisan nenek moyang dengan cita rasa tak lekang waktu. Tumpeng nasi kuning biasanya tersaji bersama dengan berbagai jenis lauk penggoda lidah. Selain tumpeng nasi kuning, jajanan pasar tradisional ini tentu sulit untuk Anda tolak. Kaya rasa, kaya warna, dan tentu saja kaya cerita. Pasti sulit bagi Anda untuk melupakannya. Balai Kambang adalah fasilitas umum berupa hutan kota di tengah kota Solo. Taman seluas 10 hektar ini adalah peninggalan Kanjeng Gusti Pangeran Adipati Aryo Mangkunegoro VII sebagai hadiah bagi kedua putri kembarnya Gusti Raden Ayu Partini dan Gusti Raden Ayu Partinah. Taman Balai Kambang terbagi dalam dua bagian dengan fungsi sebagai paru-paru kota dan resapan kota. Hutan Partinah Bosch dan Taman Air Partini Twin, nama kedua area tersebut. Taman Balai Kambang berdiri sejak tahun 1921 dengan memadukan konsep Jawa dan Eropa. Predikat kota paling layak huni menjadi kebanggaan bagi kota Solo. Pemerintah Kota Surakarta pun terus berupaya menata dan melengkapi fasilitas kota agar semakin nyaman untuk tinggal. Salah satunya adalah pendirian Taman Cerdas di beberapa lokasi. Taman Cerdas menjadi tempat untuk belajar berbagai hal, mulai dari ilmu pengetahuan, seni dan budaya, serta pengetahuan umum. Taman Cerdas juga berfungsi sebagai tempat berinteraksi yang nyaman dan bermanfaat. Taman Cerdas Jebres misalnya, menyediakan berbagai fasilitas untuk belajar berbagai hal. Di malam hari, Anda masih dapat menikmati keindahan kota di tepian Sungai Bengawan Solo ini. Di kawasan Jalan Gatot Subroto terdapat destinasi menarik di malam hari, mural. Untuk berwisata di tempat ini, Anda harus menunggu toko-toko di kawasan bisnis ini tutup. Geliat bisnis tengah kota pun berubah menjadi lukisan-lukisan cantik dengan tema-tema menarik. Swafoto menjadi aktivitas jamak bagi pengunjung mural Gatsu. Tapi, tak sedikit pula yang menikmati malam dengan bersantai sembari memandang karya seniman-seniman mural ini.
abote kangen tak songgo ana jero dodo sing tak suwun sliramu mireng lan perso endahe gending tresnoku ngelangu teng rasa melangkah dari bayangan kala aku pulang terkenang kisah kita bersama mengingat jalan yang panjang pernah kita tempuh namun badai memisahkan. Indah angin godong melung rasa abote kangen sasonggo ono jero dada sing tak suwung sliramu mireng lan perso endahe gending tresnoku ngelangu teng rasa berkhayal tentang dirimu telahkah berubah kopi ireng. Dinda di mana?
Kapan pulang? Mama kangen.
Ini tempat terbaik yang pernah kusinggahi. Hawanya mengingatkan aku pada kebahagiaan yang aku kasihi berada di kota ini. Harumnya selalu memanggilku untuk pulang. Hidup begitu ringan terasa saat ku di sini. Lepas penatku dalam pelukan kota Solo. Kamulah saksi bisu keringat dan air mataku. Tak pernah tidur hingga ku terasa sepi. Sederhanamu buatku jatuh hati. Selalu ingin pulang ke Solo. Jalan hidup membawaku terus melaju, mengalir sampai jauh bagai bengawan Solo. Tapi kau ajarkan aku jadi bijaksana, bersahaja dan menikmati anugerah Maha Esa. Hidup begitu ringan terasa saat ku di sini. Lepas penatku dalam pelukan kota Solo. Kamulah saksi jatuh hati, selalu ingin pulang ke Solo. Kamulah saksi bisu, keringatkan air mataku. Tak pernah tidur hingga ku terasa sepi. Sederhanamu buatku jatuh hati. Oh, kamulah saksi bisu, keringatkan air mataku. Tak pernah tidur hingga ku terasa sepi. Sederhanamu buatku jatuh hati, selalu ingin pulang ke Solo. Aku rindu padamu, rindu pulang ke Solo.
rasa tan kuwawa kangen marang keluarga lunga atuh saka desa golek sandang lan pokok pirang-pirang taun tak lakoni kanthi dina lawan sasi kapan gongku amung kasih aku kangen paling desa kangen anak lan keluarga aku kangen paling desa romo ibu nyuwun donga aku kangen paling desa ingkang putra Mulira Harjo ya lelungan ki iso nganggo kangen barang ta ya nah sok meneh iki nek lunga ki sangu sik tak nyanyi kangen kang tan powinates ing patenmu tansah gerantes ade kang bisa paringmu sodo alamun iso bali desa pirang-pirang taun tak lakoni dina-dina mangan ati mbuh kapan enyong bisa bali aku kangen bali desa kangen anak lan keluarga
berhubung kita di Kota Solo tercinta, spesial untuk Anda semua, Kota Solo.
Kota Surakarta atau Kota Solo adalah kota dengan segudang daya tarik untuk menjadi pilihan kunjungan Anda. Dengan potensi kekayaan seni dan budayanya, tentu saja Kota Solo menjadi pilihan tepat bagi Anda untuk berwisata. Selain itu, Kota Solo terus berbenah untuk menjadi kota meeting, insentif, convention, exhibition, MICE. Nah, di Kota Solo Anda tak hanya dapat menggelar pertemuan di gedung-gedung pertemuan saja. Saat ini pemerintah Kota Surakarta telah menyediakan bis dengan desain khusus sehingga dapat menjadi tempat meeting yang nyaman. Gatot Kaca Meeting Bus menyediakan berbagai fasilitas untuk kenyamanan meeting Anda sembari menyusuri jalanan Kota Solo. Bis berkapasitas 15 orang ini menawarkan pengalaman berbeda untuk meeting Anda. Sebagai kota jasa wisata, di Kota Solo Anda dapat menemukan tempat-tempat wisata dengan berbagai warna. Mengunjungi Lokananta tentu menjadi destinasi menarik saat berada di Kota Solo. Menjelajah setiap sudut Lokananta seolah memanjakan imaji Anda pada romantisme masa lalu, jagat hiburan Nusantara. Berdiri sejak tahun 1956, Lokananta adalah perusahaan rekaman musik pertama dan satu-satunya milik negara. Di Lokananta tersimpan ribuan keping piringan hitam berisi rekaman lagu para pesohor bersuara emas seperti Waljinah, Gesang, Titik Puspa, Bing Slamet, dan Sam Saimun. Selain lagu-lagu, tersimpan pula piringan hitam berisi pidato-pidato kenegaraan Presiden pertama Republik Indonesia, Soekarno. Berada di jantung Kota Solo, Museum Keris dapat menjadi pilihan berwisata dan mengenal salah satu kekayaan tanah air. Ribuan bilah keris dari berbagai daerah dan berbagai zaman seolah mengajak Anda untuk memutar waktu, mengenang kisah kepahlawanan di masa lalu. Di Museum Keris Anda juga dapat mengetahui bagaimana proses pembuatan keris. Diorama dan informasi detail memudahkan Anda untuk mengetahui proses tak sederhana terciptanya sebilah keris. Tak hanya kekuatan raga saja, namun juga olah rasa menjadi roh penciptaan keris. Kota Solo juga tersohor sebagai kota kuliner. Salah satu pilihan kulinernya adalah tumpeng nasi kuning. Ya, makanan berbahan dasar beras ini menjadi sajian warisan nenek moyang dengan cita rasa tak lekang waktu. Tumpeng nasi kuning biasanya tersaji bersama dengan berbagai jenis lauk penggoda lidah. Selain tumpeng nasi kuning, jajanan pasar tradisional ini tentu sulit untuk Anda tolak. Kaya rasa, kaya warna, dan tentu saja kaya cerita. Pasti sulit bagi Anda untuk melupakannya. Taman Balai Kambang adalah fasilitas umum berupa hutan kota di tengah kota Solo. Taman seluas 10 hektar ini adalah peninggalan Kanjeng Gusti Pangeran Adipati Aryo Mangkunegoro VII sebagai hadiah bagi kedua putri kembarnya Gusti Raden Ayu Partini dan Gusti Raden Ayu Partinah. Taman Balai Kambang terbagi dalam dua bagian dengan fungsi sebagai paru-paru kota dan resapan kota. Hutan Partinah Bosch dan Taman Air Partini Twin, nama kedua area tersebut. Taman Balai Kambang berdiri sejak tahun 1921 dengan memadukan konsep Jawa dan Eropa. Predikat kota paling layak huni menjadi kebanggaan bagi kota Solo. Pemerintah Kota Surakarta pun terus berupaya menata dan melengkapi fasilitas kota agar semakin nyaman untuk tinggal. Salah satunya adalah pendirian Taman Cerdas di beberapa lokasi. Taman Cerdas menjadi tempat untuk belajar berbagai hal, mulai dari ilmu pengetahuan, seni dan budaya, serta pengetahuan umum. Taman Cerdas juga berfungsi sebagai tempat berinteraksi yang nyaman dan bermanfaat. Taman Cerdas Jebres misalnya, menyediakan berbagai fasilitas untuk belajar berbagai hal. Di malam hari, Anda masih dapat menikmati keindahan kota di tepian Sungai Bengawan Solo ini. Di kawasan Jalan Gatot Subroto terdapat destinasi menarik di malam hari, mural. Untuk berwisata di tempat ini, Anda harus menunggu toko-toko di kawasan bisnis ini tutup. Geliat bisnis tengah kota pun berubah menjadi lukisan-lukisan cantik dengan tema-tema menarik. Swafoto menjadi aktivitas jamak bagi pengunjung mural Gatsu. Tapi, tak sedikit pula yang menikmati malam dengan bersantai sembari memandang karya seniman-seniman mural ini.
abote kangen tak songgo ana jero dada sing tak suwon sliramu mireng lan perso endahe gending tresnaku ngelangu teng rasa melangkah dari bayangan kala aku pulang terkenang kisah kita bersama mengingat jalan yang panjang pernah kita tempuh namun badai memisahkan kopi kopi Dinda di mana?
Kak, kapan pulang? Mama kangen.
Ini tempat terbaik yang pernah kusinggahi. Hawanya mengingatkan aku pada kebahagiaan yang aku kasihi berada di kota ini. Harumnya selalu memanggilku untuk pulang. Hidup begitu ringan terasa saat ku di sini. Lepas penatku dalam pelukan kota Solo. Kamu hati selalu ingin pulang ke Solo. Jalan hidup membawaku terus melaju, mengalir sampai jauh bagai bengawan Solo. Tapi kau ajarkan aku jadi bijaksana, bersahaja dan menikmati anugerah Maha Esa. Hidup begitu ringan terasa saat ku di sini. Lepas penatku dalam pelukan kota Solo. Kamulah saksi bisu Air mengalir sampai jauh, akhirnya ke laut. Itu perahu. Riwayatku dulu, kau pedagang selalu naik itu perahu. Bengawan Solo, riwayatku ini sedari dulu jadi perhatian insani. Musim kemarau tak berapa airmu, di musim hujan air meluap sampai jauh.
Mata airmu dari Solo terkurung gunung seribu. Air mengalir sampai jauh, akhirnya ke laut. Itu perahu.
Riwayatku dulu, kaum pedagang selalu naik itu perahu. Kaum pedagang selalu naik itu perahu. Bengawan Solo, riwayatku ini sedari dulu jadi perhatian insani. Musim kemarau tak berapa airmu, di musim hujan air meluap sampai jauh. Mata airmu dari Solo terkurung gunung seribu. Air mengalir sampai jauh, akhirnya ke laut. Itu perahu. Riwayatku dulu, kaum pedagang selalu naik itu perahu. Bengawan Solo, riwayatku ini sedari dulu jadi perhatian insani. Musim kemarau
tak berapa airmu di musim hujan air meluap sampai jauh. Mata airmu dari Solo terkurung gunung seribu. Air mengalir sampai jauh, akhirnya ke laut. Itu perahu riwayatku dulu, kaum pedagang selalu naik itu perahu. Kaum pedagang selalu naik itu perahu. Sama.